The universe is 93 billion light-years wide. It is also 13.8 billion years old, and according to the rules of physics we have spent centuries perfecting, those two numbers should not be possible at the same time. Light has a speed limit. Nothing moves faster. And yet the edge of everything we can see is sitting 46.5 billion light-years away in every direction, far beyond the distance light should have been able to travel in the time the universe has existed. That is not a rounding error. That is not a measurement glitch. That is the shape of reality, and for a long time we convinced ourselves we understood why. Then the James Webb Space Telescope turned on. What it found in the first light of creation has fractured that understanding. Galaxies that are too big, too bright, too organized, sitting in an epoch when the cosmos was barely 300 million years old. Black holes that weigh billions of solar masses, grown to impossible size in a universe that had not yet learned how to build stars efficiently. And behind it all, a population of objects so vast, so densely packed into the fabric of space, that our best estimates have jumped from 200 billion galaxies to over 2 trillion, and we are still counting. This is not just about seeing farther. This is about realizing that the universe we thought we mapped, the timeline we thought we understood, the models we built to explain how everything grew from nothing, all of it is being rewritten in real time by a telescope that refuses to show us what we expected. So how did we get the size of everything so wrong? And what does it mean when the most powerful instrument humanity has ever aimed at the sky keeps finding things that should not be there? This is that story. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. The universe is 13.8 billion years old. That number comes from decades of careful measurement, from mapping the cosmic microwave background, from tracking the expansion rate, from counting the ages of the oldest stars we can find. 13.8 billion years. Nearly 14 billion trips around the sun, if the sun had been there since the beginning, which it wasn't. The number is solid. It's one of the few things in cosmology that doesn't come with an asterisk the size of a footnote. And the observable universe, the bubble of space from which light has had time to reach us since the Big Bang, is 93 billion light-years across. Stop right there. Read that again. The universe is 13.8 billion years old, and it's 93 billion light-years wide. If you just felt something in your brain hiccup, good. That means you're paying attention, because those two numbers should not fit together. They contradict each other in a way that seems to violate one of the most fundamental rules we have about reality. Nothing travels faster than light. Not information, not matter, not causality itself. Light moves at 299,792 kilometers per second, and that speed limit is baked into the structure of space-time. It's not a suggestion. It's not a speed we haven't beaten yet because our rockets aren't good enough. It's the maximum rate at which anything in the universe can move from one point to another through space. So if the universe is 13.8 billion years old, and light has been traveling since the beginning, then the farthest light should have been able to reach us is 13.8 billion light-years. The edge of the observable universe should sit at a distance of 13.8 billion light-years in every direction. The total width, measuring all the way across through the middle, should be 27.6 billion light-years. That's the answer you get when you trust your intuition, when you do the arithmetic that feels right, when you assume the universe plays fair. The real answer is 93 billion light-years, not 27, not 30, 93. More than 3 times wider than it has any right to be. And that gap, that enormous mismatch between what the numbers should say and what they actually say, is not a mistake. It's not a typo in a textbook. It's a signpost pointing directly at something strange happening underneath everything we can see. The universe has been cheating, and understanding how it cheats is the key to understanding what the universe actually is. Let's start with what most people assume. You're standing here, on Earth, right now, in the present moment. The Big Bang happened 13.8 billion years ago. At that moment, everything that would become the observable universe was packed into an unimaginably small, hot, dense state. Then it exploded, not into space but as space. The expansion began and light started traveling. Photons raced outward in every direction at the speed of light, and they've been racing ever since. If you imagine the universe as a giant sphere with Earth somewhere near the middle, and you picture light crawling outward from the Big Bang at 299,792 kilometers per second for 13.8 billion years, you'd expect the edge of that sphere to sit 13.8 billion light years away. That's the setup, that's the intuitive model, and it makes perfect sense, except it's wrong, because it assumes the space those photons were traveling through stayed the same size while they traveled. It didn't. Space itself has been expanding the entire time. Not just the stuff in space, not just galaxies drifting apart like ships leaving a harbor. The space between the galaxies, the fabric, the grid, the stage on which everything sits, has been stretching, and as it stretches, it carries everything embedded in it farther apart. The galaxies aren't racing through space. They're standing still, and space is pulling the floor out from under them in every direction at once. Picture a balloon. Draw 2 dots on its surface with a marker, then start inflating it. The dots move apart, but they're not sliding across the rubber. The rubber itself is stretching, and the dots are just going along for the ride. The farther apart the dots start, the faster they separate as the balloon inflates, even though neither dot is actually moving relative to the surface it's sitting on. That's not a perfect analogy. The universe isn't the surface of a balloon, it's the whole volume, and there's no outside for it to expand into. But the core idea holds. Space stretches and distances grow even when nothing is moving. Another way to think about it, imagine 2 ants standing on a rubber band. They start 1 centimeter apart. Now you grab both ends of the rubber band and pull, stretching it to twice its original length. The ants are now 2 centimeters apart. They didn't walk, they didn't fly. The space between them doubled because the thing they were standing on doubled. If you keep stretching the band while one ant tries to walk toward the other, the ant might make progress for a while, but if you pull fast enough, the distance between them will grow faster than the ant can walk. The ant isn't moving backward, it's walking forward. But the rubber band is stretching faster than the ant can compensate. That's what happened to light in the early universe. Photons left their source, racing outward at the speed of light. But the space they were traveling through was expanding behind them, and in some cases expanding faster than light could cross it. That doesn't mean the photons were moving backward. It means the finish line was being dragged away from them faster than they could reach it. For billions of years, some of these photons were stuck, making forward progress, but still getting farther from their destination because the destination was receding. Eventually, the expansion rate slowed enough that the photons started making net gains, and after billions of years, they reached us. By the time they arrived, the galaxy that emitted them had been carried much, much farther away. We see the light from when it was close, but the source is now sitting 46 billion light-years away in one direction. There's another galaxy 46 billion light-years away in the opposite direction. Add those two distances together and you get 92 billion light-years, close enough to the 93 billion figure that the difference is just rounding and newer measurements tightening the numbers. The key point is this: the light travel time and the current distance are not the same thing. When we look at a galaxy whose light has been traveling for 13 billion years, we are seeing it as it was 13 billion years ago. But that galaxy is not 13 billion light-years away right now. It's much farther. Space has been stretching the whole time, and the galaxy has been carried along with it. The light bridged a gap that was shorter when it started, and by the time it finished, the gap had grown into something much wider. This is not a violation of relativity. Einstein's equations allow for this. The rule is that nothing can move through space faster than light, but space itself can expand as fast as it wants. There's no speed limit on the stretching of space-time. Galaxies at the edge of the observable universe are receding from us faster than the speed of light right now, and that's fine. They're not moving through space at that speed. Space is expanding and they're embedded in it. Relativity doesn't care. The edge of the observable universe sits at what cosmologists call the cosmic horizon. That's the boundary beyond which light has not had enough time to reach us since the Big Bang. If a galaxy sits beyond that horizon, we will never see it. Not because it's too dim, not because our telescopes aren't good enough, but because the light hasn't arrived yet. And depending on how the expansion continues, some of that light may never arrive. There are regions of space so far away, receding so quickly, that the light leaving them today will never reach Earth, even if we wait forever. The cosmic horizon isn't just a boundary in space, it's a boundary in possibility. The number 46, 5 billion light-years, is the radius of the observable universe. That's how far the current edge sits in any direction you look. Double it and you get 93 billion light-years, the full diameter, the width of the bubble we live inside. Everything outside that bubble is invisible, not because it doesn't exist, but because we are causally disconnected from it. We cannot see it, we cannot touch it, and no information from it can ever reach us. It might as well be a separate universe. Most people, when they first hear about the Big Bang, picture an explosion happening somewhere, a center point where everything started, with galaxies flying outward into empty space like shrapnel from a bomb. That picture is completely wrong. The Big Bang didn't happen at a location. It happened everywhere. Every point in space was part of the initial state. The explosion wasn't into space, it was of space. There is no center. There is no edge where the universe stops and something else begins. If you could somehow travel far enough in any direction, you wouldn't hit a wall. You'd just keep finding more universe, more galaxies, more space stretching endlessly in every direction. The observable universe is only the part we can see, the part where light has had time to reach us. The actual universe, the whole thing, could be vastly larger. It could be infinite. We don't know. We can't know. The horizon blocks our view. The James Webb Space Telescope, which launched in December 2021 and began science operations in mid-2022, was built specifically to look at the farthest, oldest, faintest objects the universe has to offer. It sits about 1.5 million kilometers from Earth, far beyond the interference of our planet's atmosphere and heat, staring into the infrared with a mirror 6.5 meters across, coated in gold. Infrared is the key. As light from distant galaxies travels through expanding space, the wavelengths stretch. A photon that started as ultraviolet gets pulled into visible light, then into red, then into infrared. The farther away the source, the more the light has been stretched, and the redder it appears. Astronomers call this redshift, and it's the primary tool for measuring cosmic distances. Webb's job is to catch that light, the most redshifted light possible, the photons that left their sources when the universe was only a few 100 million years old. These galaxies are so distant that their light has been traveling toward us for more than 13 billion years. By the time it reaches Webb's mirror, the galaxies themselves have been carried by expansion to distances far beyond 13 billion light-years. We see them as they were, tiny and young, but they are not where we see them anymore. They are somewhere much farther away, possibly grown into massive systems, possibly long dead. We will never know. The light from their current state won't reach us for billions of years, if it ever does at all. When you look at a star in the night sky, you are seeing it as it was when the light left. If the star is 10 light years away, you see it as it was 10 years ago. If it exploded yesterday, you won't know for 10 years. You are looking backward in time. The farther you look, the further back you see. Webb is looking so far that it's seeing the universe as it was in its infancy, when the first galaxies were just beginning to form, when the hydrogen gas left over from the Big Bang was first collapsing into stars. These are the earliest objects we can possibly observe, sitting at the edge of the cosmic horizon, their light stretched to the limit of what our instruments can detect. And what Webb has found is not what anyone expected, because the galaxies sitting at that edge, the ones forming just a few 100 million years after the Big Bang, are not small and dim and primitive. Some of them are enormous. Some of them are shining with the light of billions of stars, far more massive than they have any right to be at that stage of cosmic history. According to the standard model of cosmology, galaxies were supposed to grow slowly, piece by piece, over hundreds of millions of years. The early universe should have been messy, chaotic, full of small clumps of gas, struggling to pull themselves together under gravity. Instead, Webb is finding galaxies that look like they skipped the tutorial, fully formed structures sitting in an era when they should barely exist. And that's a problem, because if galaxies can grow that fast, that early, then something in our model is wrong. Either we're missing a mechanism that allows them to assemble more quickly than we thought, or the conditions in the early universe were different than we assumed. Either way, the clean story we've been telling for decades has started to crack. The cosmic paradox, the mismatch between the universe's age and its size, is not a flaw in the theory, it's a feature. The expansion of space is real, measurable, and essential to understanding how we got here. But it also means that when we look outward, we're not just looking across distance, we're looking backward through time into a universe that no longer exists. The galaxies we see in Webb's images are ghosts, echoes of objects that have long since moved on, grown up, or died. The light is real, the images are real, but the things they show us are gone. The universe we observe is a memory, and the farther we look, the older the memory becomes. The 93 billion light-year width of the observable universe is the size of the stage we can see. It is not the size of the theater. The full universe, the whole thing, extends far beyond our view. How far, we don't know. Whether it's finite or infinite, we don't know. Whether it loops back on itself, whether it has a shape, whether there are other bubbles like ours scattered through a larger space, we don't know. All we have is this one bubble, 93 billion light-years wide, filled with roughly 2 trillion galaxies, each containing billions or hundreds of billions of stars. And every one of those galaxies is moving, carried by the expansion, drifting farther away every second. The farthest galaxies Webb can see are not the farthest galaxies that exist. They're just the farthest ones whose light has reached us. There are galaxies farther out, galaxies we will see in 1 billion years, galaxies whose light is still on its way. And there are galaxies beyond the horizon, galaxies we will never see, galaxies whose light will never complete the journey because the space between us is expanding too quickly. Those galaxies are real. They exist right now, filled with stars and planets and maybe even someone looking back toward us, wondering the same things we're wondering. But we are invisible to each other. The horizon cuts both ways. The paradox isn't that the universe is bigger than its age suggests. The paradox is that we ever thought the two numbers should match. The universe is not a static box. It's a dynamic, expanding, evolving structure that has been growing since the moment it began. The fact that we can see as far as we can is itself extraordinary. The fact that light from the earliest galaxies has managed to cross billions of light years of stretching space and still reach our telescopes is a minor miracle of geometry and timing. A few billion years earlier, and the expansion would have been too fast. The light would never have made it. A few billion years later, and the expansion will have carried those galaxies so far away that their light will fade beyond detection. We are living in a brief window, cosmically speaking, when the universe is old enough to have interesting things in it and still young enough that we can see them. That window is closing. Billions of years from now, the expansion will have carried distant galaxies so far away that future astronomers, if any exist, will look out and see almost nothing. The sky will be darker, the universe will appear smaller. And if they don't have records from our era, they might never realize how much they're missing. Webb is looking backward into the cosmic dawn, into the moment when the lights first came on, and it's finding things that don't fit the story we thought we understood. The universe is stranger than we predicted. It grew faster than we expected. And the paradox of its size, the fact that it's 93 billion light-years wide despite being only 8 billion years old, is just the beginning of what that strangeness reveals. The James Webb Space Telescope is not looking at the universe, it's looking at history. Every photon that strikes its mirror left its source billions of years ago, carrying a message from an era when galaxies were young, stars were just beginning to forge heavy elements, and the cosmic dark ages were ending. Webb isn't observing the present. It's reading ancient light, stretched and distorted by the expansion of space, arriving now after a journey that began long before Earth existed. This is not a telescope in the way most people think of telescopes. It's a time machine. And the deeper it looks, the further back it sees. Webb launched on December 25, 2021, aboard an Ariane 5 rocket from French Guiana. The telescope folded itself into a payload faring like an impossibly complicated piece of origami, packed so tightly that engineers spent years rehearsing the deployment sequence because there would be no second chances. Once it left the ground, every motor, every hinge, every latch had to work perfectly. A single failure would turn the most expensive scientific instrument ever built into a $10 billion paperweight drifting through space. The deployment took 2 weeks, 178 release mechanisms, 50 major deployments. Each one had to trigger in the correct order or the whole sequence would collapse. The sunshield alone, a tennis court-sized structure made of 5 layers of material thinner than a human hair, required 140 separate actuators and motors to unfold. Engineers watched from the ground, helpless, as Webb pulled itself open in the vacuum of space with no possibility of intervention. When the final mirror segment locked into place and the last sunshield membrane tensioned, the relief in mission control was not polite applause, it was barely controlled chaos. Webb's destination was not an orbit around Earth. It was sent to a location called the Second Lagrange Point, or L2, about 1.5 million kilometers away on the far side of the planet from the Sun. Lagrange points are gravitational balance spots where the pull of the Earth and the Sun cancel out in just the right way that a spacecraft can sit there with minimal fuel expenditure, drifting in a slow halo orbit that keeps it stable. L2 is special for another reason. A telescope parked there has a permanent view away from both the Earth and the Sun, meaning it can stare into deep space without interference from either source of light and heat. Webb's entire backside, the side with the mirrors and instruments, faces away from the Sun at all times. The sun shield blocks everything else. The result is a permanently cold telescope, sitting in one of the quietest locations in the solar system, with nothing between it and the edge of the observable universe. The mirror is the first thing you notice in any picture of Webb. It's huge, 5 meters across, more than 2.5 times the diameter of Hubble's mirror. Collecting area matters in astronomy. Light from distant galaxies is faint, unimaginably faint. The difference between detecting a signal and missing it entirely often comes down to how much mirror surface you can aim at the sky. Webb's mirror gives it roughly 6 times the collecting area of Hubble, which translates directly into the ability to see fainter, more distant objects. But it's not a single piece of glass. It's 18 hexagonal segments, each made of beryllium and coated in a microscopically thin layer of gold. The gold is there because gold reflects infrared light better than almost any other material. Each segment weighs about 20 kilograms and is polished so precisely that if you scaled one up to the size of the United States, the largest imperfection would be less than 4 centimeters tall. Together, the 18 segments form a single enormous mirror, aligned so carefully that they function as one continuous surface. The alignment process took months. Engineers used tiny actuators on the back of each segment to adjust their positions in steps measured in nanometers, tilting and shifting each piece until the reflected light from all 18 converged into a single focused image. The mirror had to be segmented because there was no other way to fit it inside the rocket. You cannot launch a 5-meter mirror in one piece. It's too big, too fragile, too heavy. So Webb's mirror folds. The side segments hinge inward during launch, and once the telescope reaches space, they swing out and lock into place. The engineering required to make that work, to ensure the segments align perfectly after being subjected to the violence of launch and the temperature swings of space, is quietly one of the most impressive mechanical achievements of the last decade. Behind the mirror sits the Integrated Science Instrument Module, a refrigerator-sized box containing 4 instruments. 2 of them do most of the heavy lifting. The first is NIRCam, the near-infrared camera. This is Webb's primary imager, the instrument responsible for the stunning false-color pictures that have been flooding the internet since mid-2022. NIRCam detects light in wavelengths from 0.6 to 5 microns, covering the near-infrared spectrum. For reference, visible light that human eyes can see ranges from about 0.4 to 0.7 microns. NIRCam starts where human vision ends and extends deep into the infrared, capturing photons that have been stretched by cosmic expansion into wavelengths our eyes would never register. The camera has 10 individual detectors, each containing more than 4 million pixels. It can image a patch of sky the size of a grain of sand held at arm's length and resolve details down to 1/10 of an arcsecond. That's sharp enough to see a coin on the ground from 40 kilometers away. In practical terms, it means Webb can pick out individual galaxies in a crowded field where Hubble saw only blurry smudges. The second key instrument is MIRI, the mid-infrared instrument. MIRI looks even deeper into the infrared, from 5 to 28 microns, wavelengths so long that they require the instrument itself to be cooled to just 7 degrees above absolute zero. Webb's sun shield keeps the telescope cold, around 40 Kelvin on the mirror side, cold enough for most infrared work. But Miri needed to be colder, so it has its own dedicated cryocooler, a mechanical refrigerator that pumps heat away from the detectors using helium gas. Without that cooling, Miri's own thermal radiation would swamp the faint signals it's trying to detect. The instrument would be blinded by its own heat. Miri's job is to see the most redshifted light, the photons that have been stretched the farthest by expansion, the ones coming from galaxies so distant that their light has been traveling for more than 13 billion years. Those galaxies are the targets. They're the reason Webb exists. Webb also carries a spectrograph called in-IR spec, which splits incoming light into its component wavelengths, the way a prism splits sunlight into a rainbow. By analyzing where the bright and dark lines fall in a galaxy's spectrum, astronomers can identify which elements are present, how fast the galaxy is moving, how old its stars are, and how far away it sits. NIRSpec can observe 100 objects simultaneously, a staggering upgrade over older instruments that could only handle one at a time. Point it at a crowded field and it returns detailed chemical fingerprints for 100 galaxies in a single exposure. The fourth instrument, FGS/NIRIS, handles fine guidance and additional imaging, but NEI-CAM, MIRI and NEI-SPEC are the workhorses. Those three instruments are doing the science Webb was built for. Infrared is the key to everything. Visible light is fine for studying nearby objects, stars in our galaxy, planets in our solar system, anything close enough that the light hasn't been stretched much by cosmic expansion. But the farther you look, the more the light shifts. A galaxy sitting 10 billion light-years away is receding from us because space is expanding, and that recession stretches the wavelengths of the light it emits. Blue light gets pulled into red light gets pulled into infrared. Ultraviolet light, the kind emitted by young hot stars, gets stretched all the way into the near-infrared by the time it reaches us. This effect is called redshift, and it's directly related to distance. The farther away a galaxy is, the faster it's receding, and the more its light has been redshifted. Astronomers measure this with a number called Z. A redshift of Z equals 1 means the wavelength has doubled. Z equals 2 means it's tripled. The farthest galaxies Webb has observed sit at redshifts above Z equals 14, meaning their light has been stretched by a factor of 15. A photon that started as ultraviolet at 200 nanometers arrives as mid-infrared at 3000 nanometers. Hubble, which observes mostly in visible and near-ultraviolet wavelengths, simply cannot see those photons. They're invisible to it. Webb was designed specifically to catch them. The sun shield is what makes this possible. Infrared detectors have to be cold. If they're not, the heat from the instrument itself creates noise that drowns out the faint signals from space. It's like trying to hear a whisper in a room full of people shouting. The shouting is your own thermal radiation. The whisper is the distant galaxy. You have to silence the shouting or you'll never hear the whisper. Webb's sun shield is 5 layers of kapton, a material used in everything from spacecraft to high-end electronics, because it's strong, lightweight, and handles extreme temperatures without degrading. Each layer is coated with aluminum, and the 2 sun-facing layers have an additional coating of doped silicon to reflect heat. The layers are separated by gaps, and the whole structure works like a multi-stage thermal barrier. Sunlight hits the outermost layer and heats it to around 110 degrees Celsius, hot enough to boil water. But that heat doesn't conduct inward. The vacuum of space between the layers prevents conduction, and the reflective coatings bounce most of the heat back out. By the time you reach the 5th layer, the one closest to the telescope, the temperature has dropped to about -235 degrees Celsius. The temperature difference from one side of the sunshield to the other is roughly 345 degrees. That's the difference between boiling and nearly absolute zero, maintained by 5 sheets of material thinner than a human hair. Webb's sensitivity is hard to overstate. It can detect the heat signature of a bumblebee at the distance of the moon. That comparison gets thrown around in press releases, and it sounds like marketing, but it's not an exaggeration. Infrared light is just heat radiation. Anything with a temperature above absolute zero emits it. A bumblebee buzzing around on the lunar surface would be radiating a tiny amount of infrared energy, and Webb's instruments are sensitive enough to pick that up. Now scale that sensitivity to the cosmos, a galaxy 13 billion light-years away. Its light stretched and dimmed by billions of years of travel through expanding space, is emitting far less energy in our direction than a bumblebee on the moon. And Webb can see it, not as a vague smudge, but as a resolved object with structure, with color, with measurable properties that tell us what it's made of and how old it is. The concept of looking back in time is not metaphorical, it's literal. Light has a speed 299,792 kilometers per second, and that speed is finite. It takes time for light to travel from one place to another. When you look at the moon, you see it as it was about 3 seconds ago, because that's how long it takes light to cross the 384,400 kilometers between the moon and Earth. The sun is 8 light minutes away, so you see it as it was 8 minutes ago. If the sun exploded right now, you wouldn't know for 8 minutes. The light from the explosion would take that long to reach you. The nearest star beyond the sun, Proxima Centauri, is 24 light-years away. You see it as it was 24 years ago. If an alien civilization on a planet orbiting Proxima Centauri looked at Earth through a powerful telescope right now, they would see Earth as it was in early 2021. They'd have no idea the James Webb Space Telescope had launched. The light carrying that information hasn't reached them yet. Scale that up to cosmological distances, and the implications become staggering. A galaxy 1 billion light-years away appears to us as it was 1 billion years ago. A galaxy 10 billion light-years away appears as it was 10 billion years ago, back when the universe was only about 8 billion years old, younger than Earth is now. The farthest galaxies Webb can see are so distant that their light has been traveling toward us for more than 13 billion years. We are seeing them as they existed when the universe was in its infancy, less than 300 million years after the Big Bang. Those galaxies do not look like that anymore. They've had 13 billion years to evolve, to merge with other galaxies, to form new stars, to burn through their fuel. They might be dead by now. They might have collided with neighbors and been torn apart. They might have grown into massive elliptical galaxies 10 times their original size. We will never know. The light from their current state won't reach us for billions of years, if it ever reaches us at all. The images Webb captures are fossils, frozen moments from an ancient universe, preserved in the stretched and faded light that finally completed the journey. Webb's first deep-field image was released in July 2022, less than 6 months after launch. The target was a galaxy cluster called SMACS 723, and the image combined more than 12 hours of exposure time. What came back was extraordinary. Thousands of galaxies scattered across a patch of sky so small you could cover it with a grain of sand held at arm's length. Some of the galaxies were part of the cluster itself, sitting a few billion light-years away, their light distorted and magnified by the gravitational lensing effect of the cluster's mass. But behind them, farther back, were galaxies that had nothing to do with the cluster. Distant galaxies, ancient galaxies, galaxies whose light had been traveling for 13 billion years. They appeared as faint red smudges, stretched and warped by the lens in front of them, but unmistakably there. In a single image, Webb had captured more distant galaxies than Hubble's deepest surveys had found over weeks of observation. The improvement wasn't incremental, it was a leap. One widely shared claim from that period stated that a later deep-field image, combining more than 10,000 exposures, contained 797,942 galaxies. That number is dramatic, and it's been picked up by enough outlets that it's worth addressing. The figure is real, but it comes with context. The image in question is not a single Webb photograph. It's a composite combining data from multiple surveys, including both Hubble and Webb observations, processed and stacked to pull out every possible galaxy in the field. Some of those galaxies are nearby, cosmically speaking, sitting only a few billion light-years away. Some are at the edge of the observable universe. The point is not the exact count. The point is that when you aim the most sensitive infrared telescope ever built at what looks like an empty patch of sky and let it stare for long enough, you find galaxies everywhere. The universe is not empty, it's packed. And most of what's out there is too faint and too far away for us to have seen it until now. The anticipation before Webb's launch was enormous, but it came with caution. Hubble had already pushed deep into the early universe with surveys like the Hubble Ultra Deep Field and the Hubble Extreme Deep Field. Those images revealed galaxies at redshifts above z=10, dating back to within 500 million years of the Big Bang. Astronomers knew what to expect from Webb. More of the same, but better. Fainter galaxies, higher redshifts, sharper images. The Standard Model predicted that the earliest galaxies should be small, faint, irregular, cosmic toddlers, still forming, messy and unstructured. Webb would find them, photograph them, measure their properties, and confirm the timeline everyone had worked out over decades of observation. That was the plan. What Webb found instead was galaxies that looked too mature, too massive, too organized for the era they were supposed to represent. Galaxies at redshift 12, 13, 14, sitting just 200 to 300 million years after the Big Bang, shining with the light of billions of stars. Some of them had clear structures, disks and spirals that shouldn't have had time to form. Others were so luminous that the only way to explain their brightness was to assume they contained supermassive black holes already feeding at the center. Black holes that had no business existing that early because there wasn't enough time for them to grow. The discoveries kept piling up. Every deep field observation brought more impossible objects, galaxies that contradicted the models, galaxies that forced cosmologists to start asking uncomfortable questions. The record holder, as of this writing, is a galaxy called JWST Z140, confirmed in 2024 at a redshift of 1432. That places it about 290 million years after the Big Bang. The light from this galaxy has been traveling for 13.5 billion years. The galaxy itself, if it still exists, is now sitting roughly 46 billion light-years away, carried outward by the expansion of space. We see it as it was in the cosmic dawn, a time when the universe was supposed to be dark, quiet, and mostly empty. The galaxy is not small, it's not dim. It contains hundreds of millions of stars, possibly more, and it's bright enough to be detected across nearly the entire history of the universe. That should not be possible. The Standard Model does not allow for galaxies that massive, that luminous, that early, and yet there it is, sitting in Webb's data, refusing to go away no matter how many times the measurements are checked. Webb did not break cosmology. That's an overstatement you'll see in headlines, and it's not accurate. What Webb did was reveal that the early universe was more active, more efficient, more surprising than the models predicted. Galaxies formed faster, stars ignited sooner, black holes grew larger. The timeline everyone had agreed on is still mostly correct, but the details, the specifics of how things assembled in those first few 100 million years, are now open questions. And those questions matter because they point directly at gaps in our understanding of how structure forms, how dark matter behaves, and what the conditions were like in the universe's infancy. Webb's time machine is still running. Every month brings new observations, new deep fields, new spectroscopic surveys of distant galaxies. The telescope is expected to operate for at least 10 years, possibly longer if its fuel reserves hold out and its instruments stay healthy. It will keep looking backward, keep peeling away the layers of cosmic history, keep finding things that challenge the story we thought we understood. The universe's earliest moments are no longer hidden behind a wall of distance and redshift. Webb has punched through that wall, and what it found on the other side is a cosmos that refuses to follow the script. The standard model of cosmology has a name that sounds like it was designed to put you to sleep in a lecture hall: lambda CDM, lambda for the cosmological constant, a term Einstein added to his equations and later called his biggest blunder, though it turned out he was right. CDM for cold dark matter, the invisible stuff that makes up most of the mass in the universe and holds galaxies together through gravity alone. Put them together and you get lambda CDM, the framework that has guided cosmology for decades. It describes how the universe evolved from the Big Bang forward, how matter clumped together under gravity, how the first stars ignited, how galaxies assembled piece by piece over hundreds of millions of years. It is not a guess. It is built on mountains of observational data, refined through decades of increasingly precise measurements, tested against everything from the cosmic microwave background to the large-scale structure of galaxy clusters, and it works. Lambda CDM explains the universe we see today with remarkable accuracy. It predicts the abundance of light elements formed in the early universe. It predicts the pattern of temperature fluctuations in the cosmic microwave background. It predicts how galaxies cluster together on the largest scales. The model is not perfect, but it is very, very good at what it does. One of the key predictions Lambda CDM makes is about the early universe. According to the model, structure formation was supposed to be gradual. After the Big Bang, the universe was a hot, nearly uniform soup of hydrogen and helium with tiny density fluctuations, quantum ripples stretched to cosmic scales by inflation. Dark matter, which does not interact with light or normal matter except through gravity, began clumping together first, forming halos that pulled ordinary matter inward. Gas fell into those halos, cooled, and eventually collapsed to form the first stars. Those stars grouped into small proto-galaxies, irregular clumps of a few million stars at most. Over time, those proto-galaxies merged with one another, growing larger and more complex. Spiral arms formed. Central bulges grew. Supermassive black holes settled into the cores. The process took hundreds of millions of years, possibly longer. Galaxies in the early universe, within the first 500 million years after the Big Bang, were supposed to be small, messy, and dim, cosmic infants still figuring out how to pull themselves together. That was the expectation. Lambda CDM did not predict silence in the early universe. It predicted chaos, a universe full of activity, but activity on a small scale. Star formation should have been happening, but in scattered pockets, not in massive organized systems. The first galaxies should have been faint, hard to detect, barely distinguishable from the background noise. Hubble, pushing to the limits of its capability, found a few candidates at high redshifts, galaxies sitting 400 to 500 million years after the Big Bang. They looked about right, small, irregular, low in mass, exactly what the models predicted. Astronomers expected Webb to find more of the same, fainter versions of what Hubble had already seen, pushed further back in time, but fundamentally similar. The early universe should have been a nursery, not a factory. Webb pointed its mirror at the sky, and the nursery turned out to be full of adults. In the first deep-field images, released just months after the telescope began science operations, astronomers found galaxies at redshifts above 10, above 12, above 13. Galaxies sitting 300 to 400 million years after the Big Bang, an era when lambda CDM said structure should barely exist. These were not faint smudges, they were not irregular clumps, they were galaxies. Structured, luminous, massive galaxies shining with the light of hundreds of millions of stars, possibly billions. Some of them had clear spiral features, some had prominent central bulges. They looked like galaxies that should have taken 500 million to a billion years to assemble, but they were sitting in a universe that had only existed for 300 million years. The timeline did not fit, the mass did not fit, the morphology did not fit. These objects were breaking the rules. One of the earliest and most widely discussed examples is a galaxy called Galaxies Z13. The name comes from the survey that found it, the GRISM Lens Amplified Survey from Space, a program using Webb's instruments to study gravitationally lensed galaxies behind massive galaxy clusters. The Z13 part refers to its redshift, initially estimated at around 13, which places it roughly 300 million years after the Big Bang. Follow-up observations refined the measurement, and the galaxy held it was real. Not a glitch, not a closer object misidentified. A galaxy sitting at the edge of the cosmic dawn, glowing brightly enough to be detected across 13.5 billion years of expanding space. Galaxies Z13 is not a record holder anymore. Other galaxies have since been confirmed at even higher redshifts, but it was one of the first, and it set the tone for everything that followed. Astronomers looked at the data and started asking questions that had not been necessary before. How did this thing form so fast? Where did all the stars come from? How did the gas cool and collapse quickly enough to build something this massive in such a short time? Lambda CDM allows for some variation. The model is statistical, not deterministic. It describes average behavior, typical outcomes, the bulk properties of the universe. In any statistical model, there are outliers, rare objects that form earlier or grow faster than the average. A few massive galaxies in the early universe would not break lambda CDM. They would just be the tail end of the distribution, the lucky ones that happen to form in regions where dark matter halos were denser than usual, where gas infall was more efficient, where star formation ignited earlier. The problem is that Webb is not finding a few outliers. It is finding a lot of them. Every deep field observation turns up more early massive galaxies. The objects are not rare. They are common enough that the statistical models start to struggle. If these galaxies represent the tail of the distribution, then the tail is much fatter than lambda CDM predicts. And if the tail is that fat, then something about the underlying distribution is wrong. Another case is CEERS 1019. The name comes from the Cosmic Evolution Early Release Science Survey, one of the first large programs conducted with Webb after launch. CES 1019 sits at a redshift above 13, placing it in the same early era as Galaxies ZE13. What makes it particularly interesting is not just its distance, but its structure. The galaxy shows signs of being a disk, a rotating system with organized motion, not a chaotic pile of gas and stars thrown together by random collisions. Disk galaxies take time to form. They require angular momentum to be conserved as gas spirals inward, settling into a stable rotating configuration. In the modern universe, disk formation is well understood. In the early universe, Lambda CDM predicts that most galaxies should be irregular, shaped by mergers and violent star formation, not smooth rotation. Disks should come later, after things settle down. CEERS 1019 did not get the memo. It is sitting in an era when disk galaxies are not supposed to exist yet, and it is rotating anyway. The mass estimates for these early galaxies are what really set off alarms. Mass is harder to measure than brightness. A galaxy can look bright because it contains a lot of stars, or because it contains a small number of extremely luminous stars, or because it has an active galactic nucleus powered by a feeding black hole. Disentangling those possibilities requires spectroscopy, detailed observations of the galaxy's light split into its component wavelengths. Webb spectrographs can do that, and when the measurements started coming in, the numbers were uncomfortable. Some of these early galaxies were clocking in at hundreds of millions of solar masses, with a few candidates pushing toward 1 billion. For context, the Milky Way weighs about 1.5 trillion solar masses if you include dark matter, or roughly 60 billion solar masses in stars alone. A galaxy with 1 billion solar masses is not as massive as the Milky Way, but it is not small either, and it is sitting in a universe that has only had 300 million years to build it. Star formation is not instantaneous. You cannot take a cloud of gas and turn it into a galaxy overnight. The process has steps. First, the gas has to cool. Hot gas does not collapse under its own gravity because thermal pressure holds it up. Cooling takes time, and it requires the gas to radiate away energy, usually by emitting light when atoms collide and lose kinetic energy. In the modern universe, heavy elements like carbon and oxygen make this process efficient because they are good at radiating energy, but the early universe did not have heavy elements. The first generation of stars, called Population 3 stars, formed from pure hydrogen and helium. Those stars had to fuse hydrogen into heavier elements in their cores, then explode as supernovae to scatter those elements into the surrounding gas. Only then could the next generation of stars form more efficiently. This is a bottleneck. You cannot skip it. The first stars had to live and die before the universe could start building galaxies the way we see them today. And stars take time to live and die. Even the most massive stars, which burn through their fuel quickly, live for at least a few million years. Small stars can live for billions. Building up 1 billion solar masses of stars in 300 million years is not impossible, but it requires star formation rates that are much, much higher than what Lambda CDM predicts for that era. The Standard Model is not silent on this issue. There are mechanisms within Lambda CDM that could, in theory, produce more massive galaxies earlier than the baseline prediction. One possibility is that star formation in the early universe was far more efficient than it is today. In the modern universe, star formation efficiency is low. Only about 10% of the available gas in a galaxy actually turns into stars. The rest stays as gas, gets blown out by stellar winds and supernova explosions, or just sits there doing nothing. If the early universe had higher star formation efficiency, say 50% or even higher, then galaxies could have built up mass much faster. The question is why efficiency would be higher back then. One argument points to the lack of heavy elements. Without metals, the gas could not cool as easily, which sounds like it should slow things down. But it also meant the gas formed more massive stars, And massive stars produce intense radiation and strong stellar winds that compress nearby gas clouds, triggering more star formation in a runaway process. Starburst galaxies in the modern universe work this way, converting gas into stars at rates 10 or 100 times faster than normal. If the early universe was filled with mini starbursts, that could explain the rapid mass buildup. Another mechanism is enhanced gas accretion. Galaxies grow by pulling in gas from their surroundings. In lambda CDM, gas falls into dark matter halos and settles into a rotating disk or a diffuse halo around the galaxy. The rate at which gas falls in depends on the density of the surrounding environment and the depth of the gravitational potential well. In the early universe, gas was denser than it is today because the universe itself was smaller and more compact. If dark matter halos in the early universe were unusually dense, or if they formed in regions where gas was already concentrated, accretion rates could have been much higher than average. Pour gas into a galaxy fast enough, and it will form stars fast enough to build up mass quickly. Some models suggest that cold streams of gas, narrow filaments flowing directly into galaxies without being shock-heated first, could have delivered fuel at rates far above what happens in the modern universe. These cold streams are predicted by simulations, but observing them directly is nearly impossible because they do not emit much light. If they were common in the early universe, they could be the missing piece. There is also the possibility that lambda CDM is not wrong, but incomplete. The model assumes that dark matter is cold, meaning it moves slowly and clumps together efficiently, but there are other possibilities. Warm dark matter, for example, moves faster and does not clump as easily on small scales. If dark matter is warmer than lambda CDM assumes, it would suppress the formation of small halos in the early universe, which sounds like it should make the problem worse. Fewer small halos means fewer building blocks for galaxies to grow from. But it could also mean that the halos that do form are more massive to start with, giving galaxies a head start. Another idea involves self-interacting dark matter, where dark matter particles can collide with each other and exchange energy. That would change how dark matter halos collapse and how densely they pack together, which in turn changes how gas behaves inside them. These are speculative ideas. There is no direct evidence for warm or self-interacting dark matter, but the fact that they are being discussed at all shows how seriously astronomers are taking the tension between Webb's observations and the Standard Model. The broader implication is that the early universe was more active than anyone expected. Star formation rates in the first 500 million years after the Big Bang were higher, gas accretion was more efficient, and structure assembled faster. That does not mean lambda CDM is wrong. It means the parameters, the details of how the model plays out in practice, need adjustment. Think of it like a recipe. The ingredients are right, but the measurements might be off. Add a little more yeast, turn up the oven temperature, and you get bread that rises faster than the original recipe predicted. The bread is still bread. The recipe is still valid. You just learned something new about how the process works under different conditions. Lambda CDM is still the best framework we have for understanding the universe. But the early universe, the first few 100 million years, is turning out to be a more extreme environment than the baseline models accounted for. There is a phrase that keeps showing up in the papers and conference talks surrounding these discoveries: too big, too early. It is shorthand for the tension between observation and prediction. Galaxies that are too massive for the time available, too structured for the chaotic conditions that should have prevailed, too bright for the star formation rates lambda CDM predicts. The phrase has been picked up by science communicators and turned into headlines, some of which border on sensational. Webb breaks cosmology. The universe is broken. Scientists baffled. Those headlines are overstatements. Cosmology is not broken. Scientists are not baffled. They are surprised, which is different. Surprise means the data did not match the prediction, and now the job is to figure out why. That is how science works. You make a prediction, you test it, and when the test comes back different than expected, you update the prediction. The process is not a crisis, it is progress, but the surprise is real, and it is significant. Before Webb launched, there were a few theoretical papers suggesting that early galaxies might be more massive than the baseline lambda CDM models predicted. Those papers were speculative, exploring the edges of parameter space, seeing what would happen if you tweaked certain assumptions. Most astronomers expected the galaxy's Webb would find to be smaller and fainter, closer to the conservative predictions. The fact that Webb is finding the opposite, that it is consistently turning up massive early galaxies in every deep field it observes, means those speculative papers were onto something. The early universe did not play it safe. It went all in on star formation right out of the gate, and lambda CDM has to catch up. One of the more dramatic aspects of this story is how quickly it unfolded. Webb launched in December 2021. By mid-2022, it was delivering science data. By late 2022, papers were being published identifying high redshift galaxy candidates that challenged existing models. By 2023, follow-up observations were confirming those candidates and finding more. By 2024, the tension was undeniable, and entire sessions at major astronomy conferences were dedicated to trying to explain what Webb was seeing. In less than 2 years, a telescope fundamentally shifted the conversation around early galaxy formation. That is fast, even by the standards of modern astronomy, where new data can upend old ideas in the span of a single observing run. Glass Z13, Sears 1019, and the dozens of other high redshift galaxies Webb has catalogued are not anomalies anymore. They are a population, a class of objects that lambda CDM did not predict in sufficient numbers, sitting in an era when the universe was supposed to be quieter, dimmer, less organized. They are forcing cosmologists to revisit assumptions about star formation efficiency, gas cooling rates, dark matter halo assembly, and the role of feedback processes like supernova-driven winds and radiation pressure from massive stars. Every one of those assumptions was based on observations of the modern universe, extrapolated backward to the early universe, with the understanding that conditions were different but the physics was the same. Webb is showing that the extrapolation was too conservative. The early universe was not just different, it was wilder. The implications extend beyond galaxy formation. If galaxies assembled faster than expected, then the timeline for everything downstream shifts. The first heavy elements were produced earlier. The first planets could have formed earlier. The conditions for chemistry, for complexity, for life arrived sooner than the baseline models suggested. That does not mean life arose earlier. It just means the universe was ready for it earlier. The gap between possible and actual is still enormous, and nothing Webb has found changes the fact that we have exactly one example of life in the universe, and it is sitting on Earth. But the window of opportunity, the period during which the universe contained the raw materials and stable environments needed for biology, may have opened hundreds of millions of years earlier than anyone thought. There is also the matter of what these early galaxies looked like up close. Webb is seeing them from billions of light-years away, as faint red smudges stretched and distorted by cosmic expansion. The images are extraordinary, but they are not detailed. We cannot resolve individual stars. We cannot see the internal structure of the galaxies in the way we can for nearby objects. What we have are integrated measurements: the total light output, the total mass, the average properties. If you could somehow stand inside one of these early galaxies, what would you see? The night sky would be different. The stars would be younger, hotter, bluer. There would be far fewer heavy elements, which means planets, if they existed at all, would be strange. No iron cores, no rocky surfaces. Gas giants might form, but terrestrial worlds like Earth would be rare or impossible. The rate of supernova explosions would be higher because massive stars die young, and the early universe was making massive stars at a furious pace. The sky would be loud, in the sense that high-energy radiation from stellar winds and supernovae would flood the environment, making it hostile to anything fragile. If life could have started in one of these galaxies, it would have had to survive conditions far more violent than anything Earth experienced. Webb's findings are also pointing toward the next set of questions, the ones that cannot be answered with galaxy surveys alone. To understand how these early galaxies formed so quickly, astronomers need to know what was happening inside them. What were the star formation rates in different regions of the galaxy? What was the distribution of stellar masses? Were the stars clustered in dense cores or spread out across the disk? What was the gas content? And where was the gas located relative to the stars? Answering those questions requires observations at higher resolution, with instruments capable of picking apart the internal structure of high redshift galaxies. Webb can do some of that work, but it is limited by distance and the faintness of the targets. The next generation of telescopes, ground-based observatories with mirrors 30 or 40 meters across, will push further. They will resolve individual star-forming regions in distant galaxies. They will measure the velocities of gas clouds and trace how matter flows through the galaxy. They will fill in the details that Webb's broad-brush observations cannot capture. The discovery of massive early galaxies is not the end of the lambda CDM model. It is a refinement, a recalibration. The model predicted gradual growth, and Webb found rapid growth. The model predicted small irregular galaxies, and Webb found large structured ones. That does not mean the model is useless. It means the model was tuned to the wrong part of parameter space for the early universe. Adjust the star formation efficiency, adjust the gas accretion rates, adjust the feedback prescriptions. Run the simulations again with the new parameters and see if the output matches what Webb observed. If it does, lambda CDM survives. If it does not, then deeper changes are needed. But there is another layer to this story, one that connects directly to the next chapter. Because galaxies are not the only things Webb is finding in the early universe that should not be there. At the centers of some of these massive early galaxies, buried in their cores, are black holes. Not stellar mass black holes, the kind that form when a single massive star collapses. Supermassive black holes, millions or tens of millions of times the mass of the Sun, sitting in galaxies that are only a few 100 million years old. Those black holes present a different problem, one even harder to explain than the galaxies themselves. Because while you can build a galaxy quickly by cranking up star formation rates and pouring in gas, building a supermassive black hole in 300 million years requires mechanisms that lambda CDM does not provide. Black holes grow slowly. They eat matter at a limited rate, set by the physics of how gas spirals inward and heats up before crossing the event horizon. To grow a black hole to millions of solar masses in a few 100 million years, you need to start with a seed that is already enormous, far larger than any stellar collapse could produce. And nobody knows where those seeds came from. Black holes were not supposed to be in a hurry. That is the core assumption that guided astrophysics for decades. A supermassive black hole, the kind sitting at the center of nearly every large galaxy, weighing millions or billions of times the mass of the Sun, was understood to be the product of billions of years of patient accumulation. Start with a seed, something modest, maybe 100 solar masses left over from the collapse of a massive star. Feed it gas and dust over time. Let it merge with other black holes when galaxies collide. Give it a few billion years to work with, and eventually you get the monsters we see in the local universe. Sagittarius A star, the black hole at the center of the Milky Way, weighs about 4 million solar masses. M87 star, the black hole famously imaged by the Event Horizon Telescope in 2019, weighs 6.5 billion solar masses. These are giants, and they had time to become giants. The universe has been around for 13.8 billion years. Plenty of time for slow, steady growth. Then Webb pointed its instruments at the earliest galaxies it could find, and inside some of them, buried in their cores, were black holes that had no business being there. Not small black holes, not seeds still in the process of growing. Supermassive black holes, millions of solar masses, sitting in galaxies that existed only a few 100 million years after the Big Bang. Black holes that should have taken billions of years to grow, fully formed in a universe that had barely gotten started. The timeline does not work. The growth rate does not work. And the more Webb looks, the more of these impossible objects it finds. The problem is time. Time is the one resource the early universe did not have in abundance. You can speed up a lot of things in astrophysics by changing the conditions, by cranking up the temperature or the density or the rate at which gas flows into a system. But black holes grow at a rate limited by physics, and that limit is hard. When matter falls toward a black hole, it does not go quietly. It heats up, it emits radiation, and that radiation pushes back on the infalling matter, creating an outward pressure that opposes gravity. There is a balance point, a maximum rate at which a black hole can consume matter without the radiation pressure blowing the fuel away. That rate is called the Eddington limit, named after Arthur Eddington, the British astrophysicist who worked it out in the 1920s. For a black hole of a given mass, there is a maximum luminosity it can sustain, and from that luminosity you can calculate how fast it can grow. The math is straightforward. A black hole feeding at the Eddington limit doubles its mass roughly every 50 million years. Start with a seed of 100 solar masses, let it feed continuously at the maximum rate, and after 300 million years you get a black hole weighing a few thousand solar masses. Not millions, thousands. That is the problem. Webb is finding black holes weighing tens of millions of solar masses in galaxies seen when the universe was only 290 million years old. JWST 14-0, the same galaxy mentioned in the previous chapter, the one sitting at a redshift of 1432, does not just contain hundreds of millions of stars. It appears to be hosting a supermassive black hole at its center, actively feeding, bright enough in X-rays and infrared to stand out from the surrounding starlight. The black hole is not confirmed with absolute certainty yet. The spectroscopic data are still being analyzed, but the luminosity and the spectral signatures are consistent with an active galactic nucleus powered by a black hole. If that holds up, the black hole is sitting in a galaxy that formed less than 300 million years after the Big Bang. There is not enough time in that window to grow a supermassive black hole from a stellar mass seed using conventional accretion. The numbers do not close. To understand how severe the mismatch is, run the math with generous assumptions. Assume the seed black hole formed immediately after the Big Bang, which it could not have, but assume it anyway. Assume it started at 100 solar masses, which is already on the high end for a stellar collapse remnant. Assume it fed continuously at the Eddington limit for the entire 290 million years, never pausing, never running out of gas, never being disrupted by a supernova or a merger or any of the chaotic events that actually happen in the early universe. Under those perfect conditions, the black hole would grow to about 10,000 solar masses by the time JWST 14.0 appears in Webb's data. The observed black hole, if confirmed, is somewhere in the range of tens of millions of solar masses, possibly more. The gap between 10,000 and tens of millions is not a rounding error. It is a factor of 1,000 or more. Something is missing. The most conservative explanation is that the seed was not small. Maybe the first black holes in the universe did not form from stellar collapse. Maybe they formed another way. A way that bypasses the slow build-up and starts with something already massive. This idea is called direct collapse. In the standard picture, the first stars formed from clouds of primordial hydrogen and helium, collapsed under their own gravity, ignited fusion, and eventually died, leaving behind black holes weighing tens to a few hundred solar masses. Those black holes became the seeds for the supermassive monsters we see today. But there is another possibility. If conditions were just right, a massive gas cloud in the early universe could have collapsed directly into a black hole without ever forming a star. Skip the stellar phase entirely, and you get a black hole that starts at 10,000 or even 100,000 solar masses right out of the gate. Give that black hole 300 million years to feed at the Eddington limit, and you can reach tens of millions of solar masses. The timeline closes, the problem goes away. Direct collapse is not a new idea. Theorists have been discussing it since the 1970s. The question has always been whether the conditions for direct collapse actually existed in the early universe. You need a gas cloud that is massive, dense, and critically metal-free. Heavy elements like carbon and oxygen are efficient at radiating energy, which helps gas cool and fragment into smaller clumps. Fragmentation leads to star formation. If you want the cloud to collapse as a whole without fragmenting, you need to keep it hot, and that means keeping it free of metals. The very first gas clouds in the universe were metal-free by definition because no stars had died yet to produce metals. But they were also subject to intense ultraviolet radiation from nearby stars once the first generation started forming. That radiation heats the gas and can suppress fragmentation, creating conditions where direct collapse becomes possible. Some simulations suggest that a small fraction of early gas clouds, maybe 1 in 10,000, could have undergone direct collapse and formed black holes weighing 10,000 to 100,000 solar masses. If those heavy seeds existed, they solve the growth problem. You start big, feed fast, and reach supermassive scales within a few 100 million years. The trouble with direct collapse is that nobody has definitively observed it happening. The signature of a direct collapse black hole forming in the early universe would be a sudden burst of radiation from a region where no star had formed, a black hole appearing without a stellar precursor. That is hard to detect. Webb is good, but it is not sensitive enough to catch the brief flicker of a black hole forming 13 billion years ago, unless it happened to be extraordinarily bright or lensed by a foreground object. So direct collapse remains a theoretical possibility, supported by simulations but not yet confirmed by observation. It is the leading candidate for solving the seed problem, but it is not a proven solution. Another possibility is that black holes in the early universe did not grow at the Eddington limit. They grew faster. Super Eddington accretion is exactly what it sounds like. Feed a black hole at a rate higher than the Eddington limit predicts, faster than the radiation pressure should allow, and you get faster growth. This is not a free pass to ignore physics. Radiation pressure is real, and it does push back on infalling matter. But there are configurations where super-Eddington accretion can happen anyway. If the infalling gas is optically thick, meaning it is dense enough that radiation cannot escape easily, the radiation gets trapped inside the flow and does not push outward as effectively. The gas keeps falling in despite the radiation, and the black hole grows faster than the standard limit would suggest. Some models predict that black holes in the early universe could have sustained super-Eddington accretion rates for extended periods, doubling their mass every 10 or 20 million years instead of every 50 million. Cut the doubling time in half, and you gain an extra order of magnitude in growth over 300 million years. Start with a 10,000 solar mass seed, feed it at twice the Eddington rate, and you reach millions of solar masses within the available time. Super-Eddington accretion has been observed in the modern universe, though not in supermassive black holes. Ultra-luminous X-ray sources, or ULXs, are objects in nearby galaxies that emit X-rays at luminosities above what a stellar mass black hole feeding at the Eddington limit should produce. The leading explanation is that these are black holes, either stellar mass or intermediate mass, feeding at super-Eddington rates. The gas around them is dense, and the accretion flow is geometrically thick, trapping radiation and allowing faster infall. If ULXs can do it, the argument goes, then maybe black holes in the early universe could do it too. The early universe was denser, gas reservoirs were larger, and the conditions for thick accretion flows might have been more common. Super-Eddington growth is plausible. It fits the observations, but like direct collapse, it has not been proven. It is an idea that works on paper and in simulations, but the direct evidence is still thin. The third possibility is mergers. Black holes do not just grow by eating gas, they also grow by eating each other. When two galaxies collide, their central black holes eventually sink to the center of the merged system and spiral inward until they collide and merge into a single larger black hole. Mergers are common in the modern universe, and they are one of the primary ways supermassive black holes gain mass. In the early universe, galaxies were smaller and closer together, which means merger rates were higher. If black hole mergers were frequent enough in the first few 100 million years after the Big Bang, they could have accelerated growth significantly. A black hole that doubles its mass by merging with another black hole does not have to wait 50 million years. It happens as fast as the two black holes can find each other and spiral together, which depends on the dynamics of the host galaxies, but can happen on timescales of tens of millions of years or less. Stack up a few mergers in quick succession, and you can jump from thousands of solar masses to millions without relying on accretion at all. Mergers leave signatures. When two black holes collide, they emit gravitational waves, ripples in spacetime that propagate outward at the speed of light. LIGO and Virgo, the ground-based gravitational wave detectors that have been operating since 2015, have detected dozens of black hole mergers, but all of them involved stellar mass black holes, objects weighing a few tens of solar masses. Supermassive black hole mergers are different. They emit gravitational waves at much lower frequencies, too low for ground-based detectors to pick up. Detecting them requires a space-based detector, and the only mission designed for that, LISA, the Laser Interferometer Space Antenna, is not scheduled to launch until the 2030s. Once LISA is operational, it will be able to detect supermassive black hole mergers out to enormous distances, including mergers that happened in the early universe. If early black hole growth was driven primarily by mergers, LISA should see a population of merging black holes at high redshifts. Until then, the merger hypothesis is supported by simulations and indirect evidence, but it has not been directly tested. The reality is probably some combination of all three mechanisms. Heavy seeds from direct collapse give you a head start. Super Eddington accretion accelerates growth when gas is abundant. Mergers provide occasional jumps in mass when galaxies collide. None of these mechanisms operates in isolation. The early universe was chaotic, crowded, violent. Gas was everywhere. Galaxies were forming, merging, colliding. Star formation rates were high. Supernova rates were high. Feedback from stellar winds and black hole jets was carving out cavities in the gas and redistributing matter across kiloparsecs. In that environment, black holes were not growing in a vacuum. They were growing in the middle of a storm, fed by multiple processes simultaneously. Disentangling which process dominated requires detailed observations of individual systems, and Webb is starting to provide those observations. One of the more striking aspects of Webb's early black hole discoveries is where they are located. The black holes are not sitting in empty space. They are sitting at the centers of galaxies, the same massive early galaxies discussed in the previous chapter. That is not a coincidence. Black holes and galaxies grow together. They influence each other. When a black hole feeds, it does not just grow larger, it emits radiation and launches jets of high-energy particles that plow into the surrounding gas. That feedback heats the gas, sometimes blowing it out of the galaxy entirely, which shuts down star formation. This is called AGN feedback, where AGN stands for active galactic nucleus, the term astronomers use to describe a feeding black hole at the center of a galaxy. AGN feedback is one of the key mechanisms regulating galaxy growth in the modern universe. Without it, galaxies would turn all their gas into stars and end up far more massive than we observe. The black hole acts as a thermostat, turning star formation on and off by controlling how much gas stays cool and available. In the early universe, AGN feedback might have worked differently. The black holes were smaller, but the gas reservoirs were larger and denser. Feedback from a young black hole could have triggered star formation in some regions by compressing gas clouds, even as it shut down star formation in others by heating and expelling gas. The relationship between black hole growth and galaxy growth is not simple. It is not even one-directional. Galaxies feed black holes by funneling gas toward the center. Black holes regulate galaxies by heating and expelling gas. The two processes are locked in a feedback loop, each shaping the other. Observations of galaxies in the local universe show a tight correlation between the mass of the central black hole and the mass of the galaxy's central bulge. More massive galaxies have more massive black holes, and the ratio is remarkably consistent. That correlation suggests that black holes and galaxies have been co-evolving for billions of years, growing in tandem, influencing each other's development. Webb's observations are pushing that relationship back to much earlier times. The black holes it is finding in early galaxies are not small relative to their hosts. They are large, sometimes disproportionately large. In the local universe, the black hole at the center of a galaxy typically weighs about 0.1% of the total stellar mass. In some of the early galaxies Webb has observed, the black hole appears to weigh closer to 1% or even higher. That suggests the black holes grew faster than the galaxies, or that they started from heavier seeds, or both. Either way, it means the balance between black hole growth and galaxy growth was different in the early universe than it is today. The feedback loop had not yet settled into the equilibrium we see in mature galaxies. Everything was still adjusting. The growing population of early supermassive black holes is also reopening questions about intermediate mass black holes, objects weighing between a few hundred and a few 100,000 solar masses. These are the missing link between stellar mass black holes and supermassive ones. In the local universe, intermediate mass black holes are rare. A few candidates have been identified, but none have been confirmed with high confidence. The lack of intermediate mass black holes has been a puzzle for years because if supermassive black holes grow from stellar mass seeds, there should be a population of objects caught in the middle, black holes that started small and are still growing. Where are they? One possibility is that they grow so quickly that they skip the intermediate stage entirely, jumping from stellar mass to supermassive in a cosmologically short time. Another possibility is that they exist but are hard to detect because they are not feeding actively and therefore not emitting much light. A third possibility, now gaining traction thanks to Webb's findings, is that intermediate mass black holes were more common in the early universe and that many of them have since merged into larger black holes or been ejected from their host galaxies by gravitational interactions. Webb cannot directly observe intermediate mass black holes in the early universe. They are too faint. But it can observe the supermassive black holes that might have grown from them, and by studying the properties of those supermassive black holes, properties like mass, luminosity, and host galaxy environment, astronomers can infer what the seeds must have looked like. If the seeds were heavy, tens of thousands of solar masses or more, that points toward direct collapse or possibly a population of intermediate mass black holes that formed through runaway collisions in dense star clusters. If the seeds were light, a few hundred solar masses, that points towards stellar collapse and requires super-Eddington growth or rapid mergers to explain the observed masses. The data are still coming in. Every new high redshift black hole Webb detects adds another constraint, another piece of the puzzle. One of the more exotic ideas being discussed is that some of the early supermassive black holes might be primordial. Primordial black holes are hypothetical objects that formed in the first fractions of a second after the Big Bang, not from collapsing stars or gas clouds, but from density fluctuations in the early universe itself. If the density in a small region was high enough, it could have collapsed directly into a black hole before the universe had time to expand and smooth things out. Primordial black holes could have any mass, depending on the size and density of the fluctuation. Some could weigh as little as a grain of sand. Others could weigh thousands or millions of solar masses. If heavy primordial black holes existed, they would have been sitting in the universe from the very beginning, ready to start growing as soon as gas became available. That would give them a massive head start over black holes that had to wait for the first stars to form and collapse. Primordial black holes are speculative. There is no direct evidence they exist, and most of the parameter space where they could hide has been ruled out by other observations. But they have not been ruled out entirely, and the discovery of supermassive black holes in the very early universe has brought them back into the conversation. The observational challenge is distinguishing between different formation scenarios. A supermassive black hole sitting at a redshift of 14 looks the same whether it grew from a stellar mass seed, a direct collapse seed, or a primordial black hole. The black hole itself does not carry a label explaining its origin. The only way to figure out where it came from is to study its environment, its host galaxy, its mass relative to the galaxy, and the rate at which it is feeding. If the black hole is unusually massive compared to the galaxy, that suggests a heavy seed or rapid early growth. If the galaxy shows signs of recent mergers, that suggests black hole growth through collisions. If the black hole is feeding at super-Eddington rates, that shows up in the spectrum as unusually broad emission lines and high luminosity. Webb's spectrographs can measure those features, and over the next several years as the sample of high redshift black holes grows, patterns will emerge that favor one formation scenario over others. There is also the matter of how many of these early supermassive black holes exist. Webb has found a handful so far, but the surveys are still in their early stages. The telescope has only been operational for a few years, and most of its time has been spent on a mix of targets, not just high redshift galaxies. Dedicated surveys targeting the earliest epochs of the universe are ongoing, and the number of known high redshift black holes is growing. If they turn out to be common, if every deep field observation turns up multiple examples, that strengthens the case for heavy seeds or super Eddington growth. If they are rare, if only a few exist across the entire observable universe, that suggests they formed under special conditions that were not widely available. The statistics matter as much as the individual discoveries. The broader implication of Webb's early black hole findings is that the first few 100 million years of the universe were more eventful than anyone predicted. Galaxies assembled faster, stars formed faster, black holes grew faster. The universe did not ease into structure formation, it sprinted. And that sprint has left traces scattered across the sky, visible now to a telescope sensitive enough to catch the faint, red-shifted light from objects that formed when the cosmos was still in its infancy. These black holes are not just curiosities. They are signposts marking the transition from the cosmic dark ages to the era of galaxies and stars. They are the engines that helped shape the galaxies around them, regulating star formation and redistributing gas across kiloparsecs. And they are the ancestors of the supermassive black holes we see in every large galaxy today, including our own. The impossible black holes are not impossible. They are just faster than expected, heavier than expected, earlier than expected. The mechanisms that built them are still being worked out, but the objects themselves are real. They sit in Webb's data, confirmed by spectroscopy, measured in mass and luminosity, tied to the galaxies that host them, and every one of them is a challenge to the timeline we thought we understood. Black holes were not supposed to be in a hurry, but they were. And the universe, it turns out, does not care what we thought was supposed to happen. It built what it built, and now we are left to figure out how. The discovery of massive early black holes is only part of the larger picture Webb is revealing about the early universe. The galaxies themselves, the stars within them, the black holes at their centers, all of these are pieces of a single story about how structure formed in the first few 100 million years after the Big Bang. But those galaxies are not alone. They are part of a much larger population, a vast cosmic census that stretches across the entire observable universe. Billions of galaxies, trillions of stars, scattered through 93 billion light-years of space, and Webb, for the first time, is giving us the tools to count them. The universe is not empty. That much has been obvious since humans first looked up and saw stars scattered across the night sky. But empty and crowded are different things, and for most of the history of astronomy, the universe appeared to have plenty of room. Galaxies were separated by millions of light-years of dark space. The typical galaxy had perhaps a dozen close neighbors and vast stretches of nothing in between. Space felt spacious. That was the picture until very recently. Then Webb started taking pictures of what everyone assumed was empty sky, and it turned out the emptiness was an illusion. The universe, especially the early universe, is crowded, packed. Wall-to-wall galaxies stretching back to the edge of the observable horizon, most of them so faint and so distant that we never knew they were there. And the numbers, when you actually count what Webb is seeing and extrapolate outward, are staggering. Not hundreds of billions of galaxies, trillions, possibly more. The cosmos is not just bigger than we thought, it is fuller. The story starts with Hubble. The Hubble Space Telescope launched in 1990, and over the next 3 decades it produced some of the most iconic images in the history of science. One of the most famous is the Hubble Deep Field, released in 1995. The concept was simple. Pick a tiny patch of sky, a spot that looked completely empty to ground-based telescopes, and point Hubble at it for as long as possible. Let the telescope stare at that one spot, collecting every photon it could, building up an image over hundreds of individual exposures. The patch they chose was in the constellation Ursa Major, about 1/24th the width of the full moon, a speck. If you held a grain of sand at arm's length, the patch of sky Hubble was imaging would be roughly the size of that grain. From Earth it looked black, nothing there, just empty space between the foreground stars of our own galaxy. Hubble stared at that spot for 10 consecutive days in December 1995. When the exposures were combined and the data processed, the image showed roughly 3,000 galaxies, not stars, galaxies. 3,000 separate island universes, each containing billions of stars, crammed into a patch of sky the size of a grain of sand. The galaxies ranged from nearby spirals, relatively bright and well-resolved, to distant red smudges sitting billions of light-years away, their light stretched and dimmed by cosmic expansion. Some of the galaxies were so faint they were barely distinguishable from the background noise. The image was a revelation. If this one tiny random spot in the sky contained 3,000 galaxies, then the entire sky, covering all directions, must contain an unimaginable number. Astronomers did the math. Multiply 3,000 by the number of similar patches that would cover the full celestial sphere, account for the galaxies Hubble was too dim to detect, and you get an estimate. Roughly 200 billion galaxies in the observable universe. That became the standard number for the next 2 decades. 200 billion galaxies. It showed up in textbooks, museum exhibits, planetarium shows. It was the answer you gave when someone asked how many galaxies exist. Hubble followed up the original deep field with even longer exposures. The Hubble Ultra Deep Field, released in 2004, combined data from over 11 days of observation and pushed deeper, revealing nearly 10,000 galaxies in a patch of sky even smaller than the original. The Hubble Extreme Deep Field, released in 2012, combined more than 2 million seconds of exposure time over 23 days and revealed the faintest galaxies Hubble could detect, some of them sitting more than 13 billion light-years away. Every time Hubble looked deeper, it found more galaxies. The 200 billion estimate started to look conservative. Some astronomers suggested the real number might be closer to 500 billion. But the observations were hitting a wall. Hubble's instruments, as remarkable as they were, operated mostly in visible and ultraviolet wavelengths. Distant galaxies, their light redshifted into the infrared by cosmic expansion, were slipping past Hubble's view. The telescope could see the nearby universe beautifully. It could glimpse the distant universe, but it was missing most of it. Webb was built to fix that. Its instruments operate in the infrared, the exact wavelength range where distant galaxies shine brightest, after billions of years of redshift have stretched their light. Webb's mirror is larger than Hubble's, giving it more light-gathering power. Its detectors are more sensitive, and it sits in a location, Lagrange point 2, where the interference from Earth's heat and light is minimized. When Webb turned on and started taking pictures, it did not just improve on Hubble's images, it revealed an entirely different universe. A deeper one, a fuller one. A universe where the space between the galaxies Hubble could see was not empty at all. It was filled with galaxies Hubble had missed. Webb's first deep field image was released on July 12, 2022. The target was a galaxy cluster called SMACS 723, sitting about 4.6 billion light-years away. The cluster itself is interesting. It is massive enough that its gravity warps the space around it, bending and magnifying the light from galaxies far behind it. This is called gravitational lensing, and it turns the cluster into a natural telescope, amplifying the light from objects that would otherwise be too faint to detect. Webb pointed at the cluster and collected data for 5 hours. When the image was released, it showed thousands of galaxies. Some belonged to the cluster itself. Others were much farther away, lensed and distorted by the cluster's gravity into arcs and streaks of light, and scattered throughout the image. In the spaces between the bright foreground objects were faint red galaxies, distant galaxies, galaxies whose light had been traveling for more than 13 billion years, galaxies that Hubble had either missed entirely or detected only as vague smudges. The detail in Webb's image was extraordinary. Galaxies that appeared as single blobs in Hubble's data resolved into structured objects with spiral arms, bars, and visible star-forming regions. Faint background galaxies that Hubble could barely detect stood out clearly in Webb's infrared view. The improvement was not marginal, it was transformative, and the sheer number of galaxies visible in the image was higher than anyone had predicted. Estimates for the total galaxy count in that single deep field patch ranged from several thousand to tens of thousands, depending on how you defined a galaxy and how faint you were willing to go. The exact number is still being refined as astronomers comb through the data, identifying and cataloging every object. But the message was clear. Webb was seeing galaxies everywhere. Subsequent deep field observations reinforced the pattern. A composite image combining data from multiple surveys, including contributions from both Hubble and Webb, reportedly identified nearly 800,000 galaxies in a small region of sky. That number, 797,942 to be specific, has been widely circulated, and it sounds almost absurd. 800,000 galaxies in a patch of sky you could cover with your thumb held at arm's length. But the number is real, pulled from careful analysis of deep imaging data where every faint smudge and every barely detectable pixel of light has been checked and classified. Not all of those galaxies are at the edge of the universe. Many are relatively nearby, sitting only a few billion light-years away. But the fact that they are there, that they fill the frame so densely, changes the picture of what the universe looks like when you stare long enough. The implications for the total galaxy count are immediate. If Webb's deep fields are representative of the rest of the sky, and there is no reason to think they are not, then the number of galaxies in the observable universe is much higher than 200 billion. Early extrapolations based on Webb's data suggest the true number is closer to 2 trillion galaxies. Some estimates push even higher. The uncertainty comes from how you handle the faintest galaxies, the ones sitting right at the edge of detection. Are they real galaxies or just noise? Are they isolated objects or parts of larger structures that Webb cannot fully resolve? Those questions matter when you are trying to count objects across the entire observable universe, but the general trend is undeniable. More galaxies, many more. 2 trillion is not an exact figure. It is an estimate, extrapolated from what Webb sees in small patches of sky and scaled up to cover the full celestial sphere. The process is straightforward in principle. Measure how many galaxies you find per unit area in a deep field image. Multiply by the total area of the sky. Add in corrections for galaxies too faint to detect, and for the fact that some regions of the sky are blocked by the plane of our own galaxy. The math gives you a number, and that number keeps climbing as Webb's observations improve. 2 trillion is the current best guess, but it is not final. Future surveys will refine it. Deeper images will find fainter galaxies. Better statistical methods will account for the objects Webb is still missing. The number could go up. It probably will. To put 2 trillion galaxies in perspective, imagine trying to count them. If you started counting right now, 1 galaxy per second, never stopping to eat or sleep or breathe, it would take you more than 60,000 years to finish. That is longer than recorded human history, longer than the entire span of human civilization from the first agricultural settlements to the present. And you would be counting galaxies, not stars. Each of those galaxies contains billions or hundreds of billions of stars. The total number of stars in the observable universe, if you multiply 2 trillion galaxies by an average of 100 billion stars per galaxy, is somewhere in the range of 200 sextillion. That is a 2 followed by 23 zeros. You cannot visualize that number. You cannot hold it in your head. It is too large. The universe is not just big. It is incomprehensibly full. The increase from 200 billion galaxies to 2 trillion is not just a matter of better technology finding fainter objects. It is also a matter of understanding where those galaxies are and when they formed. Hubble's deep fields focused mostly on the relatively nearby universe, galaxies sitting a few billion light-years away, where the light had not been redshifted too far into the infrared. Webb is looking farther back, into the era when the universe was 1 or 2 billion years old, and finding that the galaxy population at those distances is much denser than expected. The early universe was not a sparse scattering of proto-galaxies slowly assembling over time. It was crowded. Galaxies were packed closer together because the universe itself was smaller. Space has been expanding for nearly 14 billion years, carrying galaxies apart. But in the early universe, before much expansion had occurred, everything was closer. The average distance between galaxies was shorter. The likelihood of interactions, collisions, and mergers was higher. The universe was a busier place. That crowding has consequences. When galaxies are close together, they do not just sit there ignoring each other. Gravity pulls them toward one another. Small galaxies merge into larger ones. Gas streams from one galaxy to another, triggering bursts of star formation. Supermassive black holes at the centers of colliding galaxies spiral inward and merge, releasing gravitational waves and jets of high-energy particles. The rate at which these interactions happen depends on the density of the galaxy population. More galaxies per unit volume means more interactions. Webb's observations, showing that the early universe contained far more galaxies than previous surveys detected, imply that the interaction rate was much higher than older models assumed. Galaxies were not growing in isolation. They were growing in a crowd, constantly bumping into neighbors, exchanging matter, merging and reshaping themselves in the process. This is not a small correction to the story of galaxy formation. It is a fundamental shift in how we understand the process. The old picture, based on Hubble's observations and the assumption that faint galaxies were rare, suggested that most galaxies grew slowly, accreting gas over time and forming stars at a steady rate. Mergers happened, but they were relatively uncommon, major events that disrupted the galaxy and triggered temporary bursts of star formation before things settled back down. The new picture, emerging from Webb's data, suggests that mergers were not rare, they were routine. Galaxies in the early universe were interacting constantly, and much of their growth came not from slow, steady accretion, but from rapid, chaotic mergers. The Milky Way itself, our home galaxy, has absorbed dozens of smaller galaxies over its lifetime. Webb's observations suggest that kind of cannibalism was even more common in the early universe, when galaxies were closer together and the supply of merger candidates was larger. The density of the early universe also affects the rate at which gas flows into galaxies. Gas does not just sit in intergalactic space waiting to be pulled in by gravity. It moves, streams along filaments of dark matter, piles up in dense regions, and gets stripped away by interactions with other galaxies. In a crowded environment, gas streams are shorter and more direct. Galaxies can pull in fuel from their surroundings more efficiently because the fuel is closer. This accelerates star formation, which helps explain why Webb is finding massive galaxies so early. The galaxies were not just growing fast because star formation was more efficient. They were growing fast because they had more gas to work with, and the gas was easier to access. The crowding fed the growth. Webb's deep fields also reveal structure on scales larger than individual galaxies. When you look at a Webb image, you do not see galaxies scattered randomly across the frame. You see patterns. Galaxies cluster together in groups. Groups cluster together in larger structures called filaments, long, thin threads of galaxies stretching across millions of light years. The filaments connect at nodes, dense regions where dozens or hundreds of galaxies pile up. The overall pattern looks like a web, which is why cosmologists call it the cosmic web. The cosmic web is not unique to the modern universe. It existed in the early universe too, but it was harder to see because the galaxies were fainter, and the observations were not sensitive enough to pick out the faint filaments. Webb is changing that. Its deep field images show the cosmic web extending back to within a few 100 million years of the Big Bang. The structure was already there, already shaping how galaxies formed and where they clustered. The universe did not start uniform and slowly develop structure over time. It started with structure, faint but present, and that structure grew and amplified as gravity pulled matter into denser and denser concentrations. The statistical implications of Webb's findings are significant. Before Webb, the sample of high redshift galaxies, objects sitting more than 10 billion light-years away, was small. Hubble had found a few hundred candidates, and follow-up observations confirmed some of them, but the sample was limited. Astronomers could not draw strong conclusions about the typical properties of early galaxies because the dataset was too sparse. Webb has changed that. In just a few years of operation, it has added thousands of high redshift galaxies to the sample, providing a much richer statistical picture of what the early universe looked like. With more data, astronomers can measure the distribution of galaxy masses, the range of star formation rates, the fraction of galaxies that are actively forming stars versus those that have already burned through their gas. Those measurements feed directly into models of galaxy formation, allowing theorists to test their predictions against a much larger and more representative dataset. One of the more surprising findings from Webb's deep fields is how many of the faint, distant galaxies look mature. Mature, in this context, means they have clear structures, well-defined disks or bulges, organized spiral arms, and relatively low levels of ongoing star formation. In the standard picture, galaxies in the early universe should be messy, irregular, dominated by chaotic star formation and frequent mergers. Mature-looking galaxies should come later, after the universe has had time to settle down. But Webb is finding structured galaxies sitting at redshifts of 10, 11, 12 epochs, when the universe was less than 500 million years old. Some of these galaxies look like smaller versions of the Milky Way, with clear rotation and organized features. That should not be possible if galaxies take hundreds of millions of years to settle into stable configurations. Either the galaxies are settling faster than expected, or they are not as mature as they appear, and the structures we are seeing are temporary features that will be disrupted by future mergers. Disentangling those possibilities requires more data, but the fact that the question is even being asked shows how much Webb has shifted the baseline expectations. Another aspect of Webb's deep fields that has drawn attention is the color distribution of the galaxies. Galaxies are not all the same color. Young galaxies full of hot blue stars and active star formation appear blue in optical images. Older galaxies where star formation has slowed or stopped and the remaining stars are cooler and redder appear red. The balance between blue and red galaxies tells you something about the overall history of star formation in the universe. In the modern universe, there are plenty of both, blue star-forming galaxies and red dead galaxies, but in the early universe, based on Hubble's observations, most galaxies were blue. That made sense. The universe was young, gas was abundant, star formation was everywhere. Webb's deep fields confirm that most early galaxies are blue, but they also reveal a population of red galaxies, objects that appear to have already stopped forming stars by the time the universe was only 1 billion years old. Those galaxies are rare, but they exist, and their existence is puzzling. How do you shut down star formation in a galaxy that early? One possibility is feedback from a supermassive black hole. The black hole heats or expels the gas, starving the galaxy of fuel. Another possibility is that the galaxy burned through its gas supply so quickly that it simply ran out. Either way, the red galaxies are outliers, objects that evolved faster than the typical galaxy, and they provide clues about the range of possible evolutionary paths galaxies can take. The crowding revealed by Webb's deep fields also has implications for the fate of those galaxies. Galaxies in dense environments do not stay isolated. They interact, merge, and eventually become part of larger structures. In the modern universe, the descendants of the small crowded galaxies Webb is seeing at high redshift are the massive elliptical galaxies that sit at the centers of galaxy clusters. Those ellipticals formed through repeated mergers, cannibalizing smaller neighbors over billions of years and growing into the giants we see today. Webb is catching them in the act, imaging the early stages of that process when the galaxies were still small and the mergers were just beginning. Following those galaxies forward in time, watching how they grow and change, is not something Webb can do directly. Light from their future states has not reached us yet, but by comparing Webb's observations of high redshift galaxies with Hubble's observations of lower redshift galaxies and ground-based observations of nearby galaxies, astronomers can piece together the evolutionary sequence. The crowded universe Webb sees at high redshift is the starting point. The sparse universe we see today, where galaxies are separated by millions of light-years, is the end point. The expansion of space has stretched the distances, pulling galaxies apart, but the structures they built in the early universe, the clusters and filaments and superclusters, persist. There is also the matter of what Webb is still missing. The 2 trillion galaxy estimate is based on extrapolating from what Webb can see, but Webb, as powerful as it is, has limits. The faintest galaxies, the smallest dwarf galaxies sitting at extreme distances, are below Webb's detection threshold. They are there, contributing to the total mass and light of the universe, but we cannot see them yet. Future telescopes, with larger mirrors and more sensitive detectors, will find some of them. Others may remain invisible forever, too faint to detect even with the best instruments we can imagine. The 2 trillion number is a lower limit. The true count could be higher, possibly much higher, but we will never know for sure because we cannot see everything. The observable universe has a horizon, a boundary beyond which light has not had time to reach us, and everything beyond that horizon is invisible. The galaxies sitting just past the edge, the ones whose light is still on its way but has not arrived yet, are not included in the count. Neither are the galaxies sitting so far away that the expansion of space is carrying them away from us faster than light can cross the growing distance. Those galaxies exist, but they are causally disconnected from us. We will never see them, and they will never see us. The psychological impact of realizing the universe contains trillions of galaxies is hard to overstate. 200 billion was already an incomprehensibly large number, large enough that most people could not really process it. 2 trillion is 10 times larger, and the gap between those two numbers is not just quantitative, it is qualitative. The universe is not just bigger than we thought. It is more filled, more structured, more active. Every deep field image Webb produces reinforces that message. The empty spaces are not empty. The dark patches are not dark. Everywhere you look, if you look long enough and carefully enough, there are galaxies. The universe is wall-to-wall structure, stretching from the nearest neighbor galaxy, Andromeda, sitting a mere 5 million light-years away, all the way out to the cosmic horizon 46 billion light-years distant. And all of that structure, all those trillions of galaxies, formed from the same starting point, a hot, dense state 8 billion years ago, when the entire observable universe was compressed into a volume smaller than a single galaxy is today. The fact that the universe went from that state to this one, from a smooth, featureless fog to a web of trillions of galaxies, is one of the most extraordinary transformations in the history of anything. Webb's deep fields are not finished. The telescope is expected to operate for at least another decade, and during that time it will conduct more surveys, image more patches of sky, push deeper into the infrared, and refine the galaxy count even further. Each new observation adds to the statistical sample, improving our understanding of how galaxies form, how they evolve, and how they are distributed across space and time. The 2 trillion number will be updated, probably upward, as the data accumulate, and eventually future telescopes will take over, pushing past Webb's limits and finding the galaxies that Webb cannot see. The process of counting the universe is not finished. It will never be finished. But Webb has taken us further than any previous instrument, and the universe it has revealed is far richer and far more crowded than anyone expected. The crowding of the early universe connects directly to the next piece of the puzzle, because all those galaxies, all that structure, all that matter, is embedded in a space that has been expanding since the Big Bang. The expansion is not uniform, it is not constant. It has been accelerating for the last several billion years, driven by something we do not understand, something we call dark energy. And that acceleration, that mysterious force pushing space apart faster and faster, is what determines the ultimate fate of the universe and everything in it. The galaxies Webb is finding, the structures it is mapping, the cosmic web stretching across 93 billion light-years, all of it is being shaped by the expansion. And to understand the expansion, you have to understand what is driving it. The universe is not just expanding, it is accelerating. Those are two different statements, and the difference between them is the difference between a cosmos that eventually slows down and collapses back on itself, and a cosmos that flies apart forever, faster and faster, until every galaxy beyond our local neighborhood vanishes beyond an unreachable horizon. For most of the 20th century, cosmologists assumed the expansion was slowing. Gravity, they thought, was pulling everything back together, fighting the outward motion left over from the Big Bang. The universe was like a ball thrown into the air. It goes up, but gravity pulls it back down. The only question was whether the universe had enough energy to keep expanding forever, like a ball thrown so fast it escapes Earth's gravity, or whether it would eventually reverse course and collapse. Either way, the expansion was supposed to be decelerating. Gravity was supposed to be winning, or at least putting up a fight. That assumption held until 1998, when two independent teams of astronomers studying distant supernovae made a discovery that no one saw coming. The expansion is not slowing down, it is speeding up. The discovery came from observations of Type 1, a supernovae, a specific kind of exploding star that serves as a cosmic distance marker. Type 1, a supernovae, are useful because they always explode with roughly the same brightness. They are not identical, but they are close enough that astronomers can use them as standard candles. Measure how bright the supernova looks from Earth. Compare that to how bright it should be based on its known peak luminosity, and you can calculate how far away it is. Combine that distance with the redshift of the supernova's host galaxy, which tells you how fast the galaxy is receding, and you get a direct measurement of the expansion rate at different points in cosmic history. The farther away the supernova, the longer its light has been traveling, and the further back in time you are looking. By comparing nearby supernovae to distant ones, you can trace how the expansion rate has changed over billions of years. The two teams, one led by Saul Perlmutter at Lawrence Berkeley National Laboratory and the other led by Brian Schmidt and Adam Rees, were doing exactly that. They were measuring supernovae at various distances, plotting the relationship between distance and redshift, and expecting to see a curve that showed the expansion slowing over time. What they found was the opposite. The distant supernovae were dimmer than expected, which meant they were farther away than they should have been. The universe had expanded more than the models predicted. Instead of slowing down, the expansion had sped up. Somewhere around 5 or 6 billion years ago, the deceleration stopped and the acceleration began. The universe hit the gas pedal, and it has been acceleration ever since. The result was so unexpected that both teams spent months checking and rechecking their data. Supernovae are faint, and measuring their brightness accurately requires careful calibration. Dust between the supernova and Earth can dim the light, making the object look farther away than it really is. Systematic errors in the instruments can skew the measurements. Both teams ran through every possible source of error they could think of, and the result held. The supernovae were dimmer. The expansion was accelerating. In 1998, both teams published their findings. The reaction in the cosmology community was a mix of shock, skepticism, and scrambling to figure out what could possibly be driving the acceleration. Gravity pulls things together. It does not push them apart. If the expansion is speeding up, something else must be doing the pushing. Something that acts like anti-gravity, a repulsive force that gets stronger as space gets larger. That something was given a name: dark energy. Dark energy is not a substance. It is not a particle. It is not matter in any conventional sense. It is a property of space itself. The simplest way to think about it is that empty space has energy. Not a lot of energy per cubic meter, but enough that when you add it up across the entire universe, it dominates everything else. Dark energy does not clump. It does not form structures. It does not interact with matter or light. It just sits there, uniformly filling every cubic centimeter of space, exerting a gentle outward pressure. That pressure is weak on small scales. Inside a galaxy, inside a star, even inside the space between stars in a galaxy, dark energy is irrelevant. Gravity is far stronger, and it holds everything together. But on the largest scales, across millions and billions of light years, dark energy wins. There is so much space, and every bit of that space contributes a tiny amount of outward push. Add it all together, and the push becomes the dominant force in the universe. The term dark energy is a placeholder. It describes what the thing does, not what it is. Nobody knows what dark energy actually is. The leading candidate is the cosmological constant, a term Albert Einstein added to his general relativity equations in 1917. Einstein introduced the constant because he wanted his equations to allow for a static universe, one that neither expanded nor contracted. At the time, most physicists believed the universe was eternal and unchanging, and Einstein's equations without the constant predicted expansion or collapse. Adding the constant provided a repulsive force that balanced gravity and kept the universe static. Then in the 1920s, Edwin Hubble discovered that the universe was expanding. Galaxies were moving apart, and the farther away they were, the faster they were receding. Einstein reportedly called the cosmological constant his biggest blunder and removed it from his equations. The universe did not need a repulsive force if it was already expanding. Except it turns out the universe does need a repulsive force, not to keep it static, but to explain why the expansion is accelerating. The cosmological constant fits the observations almost perfectly. If you interpret it as the energy density of empty space, a fixed amount of energy per unit volume that does not dilute as the universe expands, then it produces exactly the kind of acceleration the supernova data show. As the universe grows, the total amount of dark energy increases because there is more space, and each new cubic meter of space comes preloaded with the same energy density. Matter and radiation, by contrast, get diluted as the universe expands. Spread the same amount of matter over a larger volume, and the density drops. Dark energy does not dilute, it stays constant. So as the universe gets bigger, dark energy becomes more and more dominant relative to everything else. In the early universe, matter and radiation were dense enough that their gravity overwhelmed dark energy. The expansion was decelerating, but as the universe expanded and matter diluted, dark energy caught up. About 5 billion years ago, dark energy became the stronger force, and the expansion started accelerating. It has been accelerating ever since, and it will keep accelerating forever. The amount of dark energy in the universe is staggering. Current measurements suggest that dark energy makes up about 68% of the total energy content of the universe. Dark matter, the invisible stuff that holds galaxies together, makes up about 27%. Ordinary matter, the stuff that makes up stars and planets and people, is about 5%. Everything we can see, everything we have ever touched or measured or built, is a rounding error in the cosmic budget. The universe is dominated by things we cannot see and do not understand. Dark energy is the biggest piece of that puzzle, and it is the least understood. We know it is there because we can measure its effects. We know how much of it there is because we can calculate how much energy is needed to produce the observed acceleration. But we do not know what it is made of, why it exists, or why it has the density it has. The cosmological constant is the simplest explanation for dark energy, but it comes with a massive theoretical problem. Quantum field theory, the framework that describes how particles and forces work at the smallest scales, predicts that empty space should have energy. Virtual particles pop in and out of existence, borrowing energy from the vacuum for brief moments before annihilating and disappearing. Those fluctuations contribute to the energy density of space. The problem is that when physicists calculate how much energy the vacuum should have based on quantum field theory, the answer they get is about 10 to the power of 120 times larger than the observed value. That is not a typo. 10 to the power of 120, a 1 followed by 120 zeros. The prediction is off by more than 100 orders of magnitude. This is called the cosmological constant problem, and it is one of the biggest unsolved puzzles in physics. Either quantum field theory is wildly wrong about the energy of the vacuum, or there is some unknown mechanism that cancels out almost all of that energy, leaving behind the tiny amount we observe. Nobody knows which it is. The alternative to the cosmological constant is that dark energy is not constant. Maybe it is a field, something dynamic that changes over time, getting stronger or weaker as the universe evolves. Physicists call this idea quintessence, and it allows for dark energy to have different properties at different times. In some models, quintessence could eventually decay or weaken, slowing the acceleration or even reversing it. In others, it could grow stronger, accelerating the expansion faster and faster until the universe tears itself apart in a scenario cosmologists call the Big Rip. Observations so far suggest that dark energy behaves like a cosmological constant, unchanging over billions of years, but the data are not precise enough to rule out small variations. Distinguishing between a true constant and a slowly evolving field requires extremely accurate measurements of the expansion rate at different times, and that is exactly what Webb and other telescopes are working on. Dark energy does not just drive the expansion, it defines the limits of what we can ever see. Because space is expanding, and because that expansion is accelerating, there are regions of the universe that are moving away from us faster than light can travel through space. This is not a violation of relativity. Nothing is moving through space faster than light. Space itself is expanding, carrying distant galaxies along with it, and there is no speed limit on that. The result is that light from the most distant galaxies is fighting a losing battle. It races toward us at the speed of light, but the space between us and the source is expanding faster than the light can cross it. For a while, the light makes progress. It gets closer in terms of the physical distance to Earth. But eventually, if the expansion keeps accelerating, the light stops making progress. It is running on a treadmill that is speeding up, and no matter how fast it runs, it cannot reach the finish line. This defines the cosmic horizon, also called the cosmological horizon or the event horizon of the universe. The horizon is not a physical boundary. It is the distance beyond which light will never reach us, no matter how long we wait. Galaxies sitting beyond the horizon are invisible to us, not because they are too faint or too far away in a conventional sense, but because the light they emit today will never complete the journey. The expansion is stretching the space between us faster than the light can cross it. Those galaxies are real. They exist right now. They contain stars and planets and possibly life, but they are causally disconnected from us. We cannot see them, we cannot send signals to them, and they cannot send signals to us. The horizon cuts both ways. From their perspective, we are beyond their horizon. We are invisible to them. The size of the cosmic horizon depends on the rate of expansion and how that rate changes over time. In a universe that expands but does not accelerate, the horizon keeps growing. Light that was once too far away to reach us eventually arrives as the universe ages. In a universe with accelerating expansion, the horizon stops growing and eventually starts shrinking. Galaxies that are visible to us now will cross the horizon in the future as the acceleration carries them beyond the point where their light can reach us. Billions of years from now, the sky will be emptier. Distant galaxies will fade, redshifted into invisibility as the space between us and them stretches beyond the reach of any telescope. The Milky Way and the other galaxies in our local group, bound together by gravity, will remain visible. Everything else will disappear. The current size of the cosmic horizon is about 46.5 billion light-years in every direction, giving the observable universe a diameter of 93 billion light-years. That number comes from calculating how far light could have traveled since the Big Bang, accounting for the expansion of space during that time. Light from galaxies sitting at the horizon left its source when the universe was very young, a few 100 million years after the Big Bang. That light has been traveling toward us for more than 13 billion years, but the source has been carried much farther away by expansion. The galaxy that emitted the light is now sitting roughly 46 billion light-years away, and the light we see today shows the galaxy as it was in its infancy. The current state of that galaxy, if it still exists, is invisible to us. The light carrying information about its present state has not arrived yet, and depending on how the expansion continues, it may never arrive. The horizon also defines what we mean by the observable universe. The observable universe is not the whole universe. It is the bubble of space from which light has had time to reach us. Everything inside the bubble is observable, at least in principle. Everything outside is not. The actual universe, the full extent of space and matter, could be much larger than the observable part. It could be infinite. We do not know, and we cannot know, because we cannot see past the horizon. Some cosmologists argue that the universe is infinite, stretching endlessly in all directions with no edge and no center. Others suggest it could be finite but unbounded, like the surface of a sphere where you can travel in any direction forever without hitting a boundary, but the total area is finite. Both ideas are consistent with the observations. The cosmic microwave background, the earliest light we can see, shows no sign of curvature or edges, which suggests the universe is either flat and infinite or so large that any curvature is undetectable. Either way, the part we can see is only a tiny fraction of the whole. Webb's observations are helping refine our understanding of dark energy by measuring how the expansion rate has changed over time. The more precisely we can measure distances to distant galaxies and supernovae, the better we can constrain the properties of dark energy. If dark energy is truly constant, then the expansion rate should follow a specific trajectory, accelerating at a steady pace. If dark energy is changing, the trajectory will deviate from that prediction. Webb's ability to observe galaxies at extremely high redshifts, combined with its spectroscopic instruments that can measure precise distances, makes it an ideal tool for testing dark energy models. Early results from Webb are consistent with the cosmological constant, but the data are still being analyzed, and the uncertainties are large enough that alternative models cannot be ruled out yet. One of the key measurements Webb is making is the Hubble constant at different redshifts. The Hubble constant is the expansion rate of the universe right now, measured in kilometers per second per megaparsec. It tells you how fast galaxies are receding as a function of their distance. If you measure the Hubble constant using nearby galaxies, you get one number. If you measure it using the cosmic microwave background and extrapolate forward, you get a different number. That discrepancy, called the Hubble tension, is one of the biggest unresolved issues in cosmology. Webb is measuring distances to galaxies at intermediate redshifts, filling in the gap between the nearby universe and the early universe, and those measurements are starting to show how the expansion rate has evolved over time. If the evolution does not match what the standard model predicts, it could point to new physics, possibly related to dark energy. The dominance of dark energy has profound implications for the future of the universe. In the early universe, gravity was the dominant force. Matter and radiation were dense, pulling everything together, fighting the expansion. Dark energy was there, but it was weak compared to gravity. As the universe expanded and matter diluted, the balance shifted. Dark energy became stronger, relatively speaking, because it did not dilute. Eventually, dark energy won. The expansion stopped decelerating and started accelerating, and from that point forward, the universe entered a new phase. Gravity still matters on small scales. It holds galaxies together. It holds stars together. It holds planets in orbit. But on the largest scales, across the voids between galaxy clusters, dark energy is in control. It is pushing space apart, and nothing can stop it. The acceleration has been mild so far. The expansion rate is increasing, but slowly. Over the next few billion years, the rate will continue to grow, and the effects will become more noticeable. Distant galaxies will fade as they cross the horizon. The cosmic microwave background, already faint, will redshift further until it is undetectable. Eventually, only the galaxies in our local group will remain visible. The Milky Way, Andromeda, Triangulum, and a few dozen smaller satellite galaxies, all bound together by gravity, will form an island universe surrounded by darkness. Astronomers living trillions of years from now, if any exist, will look out and see almost nothing. No distant galaxies, no cosmic microwave background, no evidence of the Big Bang. The universe will appear static, empty, and eternal. They will have no way of knowing that their island universe is drifting through a vast, expanding cosmos, because everything beyond their local group will have vanished beyond the horizon. If dark energy continues to behave like a cosmological constant, the universe will keep accelerating forever. The expansion will grow faster and faster, but it will never reach a point where it tears galaxies apart or disrupts solar systems. Gravity on small scales is strong enough to hold structures together, and dark energy, even as it grows in total influence, remains too weak on those scales to overcome it. The universe will grow colder, darker, emptier, but it will not rip apart. Stars will burn out. Black holes will evaporate. Eventually, after trillions upon trillions of years, the universe will reach a state called heat death, where all the energy has been spread so thin that nothing interesting can happen anymore. No stars, no life, no motion. Just a cold, dark, empty expanse of space stretching endlessly in all directions. If dark energy is not constant, the future could be different. If dark energy weakens over time, the acceleration could slow or stop, and the universe might eventually recollapse in a big crunch. If dark energy strengthens, the acceleration could grow so extreme that it eventually overwhelms gravity even on small scales. Galaxies would be torn apart, then solar systems, then planets, then atoms. This is the Big Rip scenario, and it is one of the more dramatic possible endings for the universe. Current observations suggest the Big Rip is unlikely, but the data are not precise enough to rule it out entirely. The behavior of dark energy over the next few billion years will determine which scenario plays out, and that behavior is something Webb and future telescopes are designed to measure. The concept of the cosmic horizon also raises philosophical questions about what it means to exist in a universe where most of reality is forever out of reach. The galaxies beyond the horizon are real. They contain stars, planets, possibly civilizations, but we will never see them. They will never see us. No signal we send, no light we emit will ever reach them. They are part of the same universe, formed in the same Big Bang, governed by the same laws of physics, but they might as well be in a separate cosmos. The horizon is an absolute boundary, not just on observation but on interaction. Causality stops at the horizon. Anything beyond it cannot affect us, and we cannot affect it. In a very real sense, the universe beyond the horizon does not exist for us. It is there, but it is inaccessible, and inaccessibility is a kind of non-existence. That boundary is not fixed. It is dynamic, moving as the universe evolves. In the past, the horizon was smaller. Galaxies that are visible to us now were once beyond the horizon. Their light had not yet reached us. As the universe aged, the horizon grew, and those galaxies came into view. In the future, the horizon will shrink. Galaxies that are visible now will cross the horizon and disappear. The observable universe is not a static bubble. It is a shifting window, expanding in some directions as light from distant sources finally arrives, contracting in others as acceleration pushes sources beyond the reach of light. We are living in a brief moment, cosmically speaking, when the observable universe is at its largest. In the deep future, it will be much smaller. In the deep past, it was much smaller. We are watching the universe at its peak, before the horizon starts to close in. The existence of dark energy means the universe will never run out of space. Space is being created continuously as the universe expands. Every second, the volume of the observable universe grows by an enormous amount, and all of that new space comes with its own dark energy. The process is self-reinforcing. More space means more dark energy, which means faster expansion, which means more new space. The universe is not running out of anything. It is growing, accelerating, becoming larger and emptier, and it will keep doing so for as long as dark energy remains the dominant force. There is no equilibrium. There is no steady state. The universe is in a runaway process, and the only way to stop it would be for dark energy to weaken or disappear entirely. So far, there is no evidence that is happening. Webb's role in understanding dark energy is indirect but critical. The telescope is not measuring dark energy directly. Nobody can. Dark energy does not emit light. It does not interact with matter. It just exerts a gentle outward pressure on space itself. What Webb can measure is the expansion history of the universe, the distances to galaxies at different redshifts, the rate at which those galaxies are receding. Those measurements, combined with data from other telescopes and experiments, allow cosmologists to infer the properties of dark energy. If the measurements show that the expansion rate is changing in unexpected ways, that could point to new physics. If the measurements confirm that dark energy behaves like a cosmological constant, that narrows down the possibilities and strengthens the case for the standard model. Either way, Webb is providing the data needed to test the models, and that is how science advances. One measurement at a time, one galaxy at a time, one step closer to understanding what is driving the universe apart. The discovery of dark energy changed cosmology in a fundamental way. Before 1998, cosmologists had a relatively simple picture of the universe. It started with the Big Bang, expanded under the influence of gravity, and would eventually either collapse or expand forever at a slowly decreasing rate. The future was uncertain, but the options were clear. Dark energy introduced a third option, one that was not on the table before. The universe is not just expanding, it is accelerating, and that acceleration changes everything. The future is no longer uncertain. It is written. The universe will expand forever, faster and faster, growing colder and emptier, until nothing remains but isolated islands of matter, drifting through an ocean of dark, empty space. That is not a guess. That is the prediction based on the best data we have. And Webb, by measuring the expansion history more precisely than ever before, is helping to confirm it. The architects of expansion are not people. They are forces, abstract and invisible, reshaping the universe on scales so large that human minds struggle to grasp them. Gravity pulls, dark energy pushes. The balance between them determines the structure of the cosmos, the size of the observable universe, and the fate of everything in it. For billions of years, gravity was winning. Dark energy was there, lurking in the background, but it was too weak to matter. Then, about 5 billion years ago, the balance shifted. Dark energy took over, and the universe entered a new phase. The cosmic horizon, the boundary of the observable universe, stopped growing. Distant galaxies started to fade. The future became clear, and all of it, every bit of it, is driven by a force we do not understand, a property of empty space that refuses to reveal its nature. Webb is staring into that mystery, one galaxy at a time, measuring the fingerprints of dark energy written across the light from distant stars. The data are piling up, the precision is improving, and slowly, piece by piece, the picture is coming into focus. We may never know what dark energy is, but we are learning what it does, and that is a start. The universe is accelerating, the horizon is shrinking, And the galaxies we see today, the trillions of islands scattered across the observable cosmos, are all we will ever have. Everything beyond them is already gone, carried away by forces we cannot stop and do not fully understand. The architects of expansion have built a universe that is vast, dynamic, and ultimately profoundly lonely. And Webb is showing us, in exquisite detail, exactly what that universe looks like before the horizon closes and the lights go out. The universe has been lying to us, not through malice or intent, but through distance and silence. For most of human history, the cosmos was a fixed backdrop, a dome of unchanging lights painted onto the vault of heaven. The stars were eternal, the universe static, and our place in it secure. Then we built telescopes. We pointed them upward, and the dome cracked open. What spilled out was a story no one predicted. A universe born in violence, exploding outward from a point smaller than an atom, expanding and cooling and building itself piece by piece over nearly 14 billion years. Hydrogen fusing into helium, helium into carbon and oxygen, stars dying, scattering heavy elements into space, seeding the clouds from which new stars would form, galaxies assembling from scattered clumps of gas, black holes growing at their centers, structure emerging from chaos, life eventually on at least one small rocky planet orbiting an unremarkable star in an unremarkable galaxy. That story held for decades. It explained the cosmic microwave background. It explained the abundance of light elements. It explained how galaxies clustered together on the largest scales. It was a good story, a clean story. And then the James Webb Space Telescope turned on and the story started to unravel. Not completely. The framework still stands. The universe is still expanding. It still started with a big bang. Dark matter still holds galaxies together. Dark energy still pushes space apart. The foundation is solid. But the details, the specifics of how things happened and when they happened and how fast they happened, those details are being rewritten in real time, and the new version of the story is stranger, faster, and more crowded than anyone expected. Recap what Webb has found in just a few years of operation. Galaxies sitting at the edge of the cosmic dawn, less than 300 million years after the Big Bang, shining with the light of hundreds of millions of stars, massive structures that should have taken a billion years to assemble, fully formed when the universe was barely out of its infancy. Organized disks and spiral arms appearing in an era when everything should have been chaotic and irregular. Black holes weighing tens of millions of solar masses sitting at the centers of those galaxies, impossibly large for the time available to grow them. A universe not just populated, but crowded, with trillions of galaxies filling every patch of sky, stretching back to the limits of what light can reach. Every one of these discoveries contradicts the conservative predictions. Every one of them pushes the timeline earlier, the masses higher, the structures more complex. The early universe was not a quiet nursery where galaxies slowly assembled over hundreds of millions of years. It was a forge, hot and violent and efficient, building massive systems in a fraction of the time the models allowed. Lambda CDM, the standard model of cosmology, has not collapsed under the weight of these discoveries. It has bent. The model is flexible enough to accommodate faster star formation, heavier black hole seeds, higher gas accretion rates. You can adjust the parameters, tweak the efficiencies, add mechanisms like super Eddington accretion or direct collapse black holes, and get results that match what Webb is seeing. The problem is that every adjustment moves you farther from the baseline prediction. The model was supposed to work with conservative assumptions, galaxies forming slowly, black holes growing at the Eddington limit, structure assembling through gradual mergers. Webb is showing that none of those assumptions held in the early universe. Everything happened faster, bigger, earlier. That does not mean lambda CDM is wrong. It means the early universe was a more extreme environment than the baseline models accounted for. The question is whether those adjustments are enough, or whether something deeper is missing. There are hints that something deeper might be missing. The Hubble tension, the mismatch between the expansion rate measured locally and the rate predicted by the cosmic microwave background, has not gone away. Webb's observations of distant supernovae and galaxies have confirmed the local measurements, widening the gap rather than closing it. Either the early universe expanded differently than the standard model predicts, or dark energy behaves differently than a cosmological constant, or there is new physics hiding in the gap. The discovery of massive early galaxies and black holes adds weight to the idea that the early universe was not behaving the way the models say it should. If galaxies can assemble that quickly, if black holes can grow that fast, maybe the conditions in the first few 100 million years after the Big Bang were fundamentally different from what we assumed. Maybe dark matter clumped together more efficiently. Maybe the first stars were far more massive and burned far more violently. Maybe there were primordial black holes scattered through the early universe, seeding the supermassive monsters we see today. These are not wild speculations. They are serious ideas being discussed in peer-reviewed journals and debated at conferences driven by the data Webb is producing. The philosophical implications of Webb's discoveries extend beyond the details of galaxy formation and black hole growth. They touch on something more fundamental: how much of the universe we can actually see and how much we are missing. The observable universe, the bubble of space from which light has had time to reach us, is 93 billion light-years across. That is not the whole universe. It is just the part we can observe. The full extent of space and matter could be vastly larger. Some estimates suggest the universe is at least 250 times bigger than the observable part. Others argue it could be infinite, stretching endlessly in all directions with no edge and no center. If inflation is correct, and the universe underwent a brief period of exponential expansion in the first fractions of a second after the Big Bang, then the observable universe is only a tiny patch of a much larger whole. Most of reality is forever out of reach, hidden beyond the cosmic horizon, causally disconnected from us. We will never see it, we will never touch it. It might as well not exist, at least not for us. That realization changes the stakes. We are not just exploring the universe, we are exploring a small corner of the universe, the only corner we will ever have access to. Everything Webb is seeing, every galaxy it images, every black hole it detects, every structure it maps, is part of that corner. The rest, the vast majority of the cosmos, is invisible. And the accelerating expansion driven by dark energy means the corner is shrinking. Distant galaxies are crossing the horizon right now, disappearing into regions of space that are receding faster than light can travel. Billions of years from now, the night sky will be emptier. The cosmic microwave background will fade into undetectability. Future astronomers, if any exist, will look out and see almost nothing. They will have no way of knowing that their tiny island of galaxies is drifting through a vast, expanding ocean of space, because everything beyond their island will have vanished beyond the horizon. They will live in a universe that appears static, eternal, and empty. They will have no evidence of the Big Bang, no evidence of cosmic expansion, no evidence that the universe was ever different than it is in their time. All the knowledge we are gathering now, all the discoveries Webb is making, will be lost to them unless we leave records they can find. That future is not imminent. It is trillions of years away, an unimaginably distant era when the stars have burned out and the black holes have evaporated and the universe has settled into its final cold, empty state. But the process has already begun. The horizon is already shrinking. Galaxies are already crossing it. We are living in a brief window, cosmically speaking, when the universe is old enough to have interesting structures and still young enough that we can see them. That window is closing. Not quickly, not in any time frame that matters to human civilization, but it is closing. And the fact that it is closing means the universe we observe today is not the universe future observers will see. The cosmos is dynamic, evolving, and the part of it we can access is shrinking with every passing second. Webb's contribution to this story is not just the data it is collecting, it is the shift in perspective those data force. Before Webb, the early universe was a theoretical construct, a set of equations and simulations extrapolated backward from the present. We knew galaxies must have formed at some point. We knew the first stars must have ignited. But we did not have pictures. We did not have spectra. We did not have direct measurements of what those early galaxies looked like, how massive they were, how fast they were forming stars. Webb has turned the early universe from a hypothesis into an observable reality. The galaxies are there, the black holes are there, the structures are there, and they do not match the conservative predictions. The early universe was not cautious, it was reckless. It built massive galaxies and supermassive black holes in a cosmic eye blink, and it did so under conditions that should have made that process slow and difficult. Understanding how that happened is the next frontier. The new questions Webb has raised are as important as the discoveries it has made. How did the first black holes form? Were they remnants of the first generation of stars, or did they form through some other mechanism, direct collapse, or primordial seeds left over from the Big Bang? How did galaxies assemble so quickly? Was star formation more efficient in the early universe, or were gas accretion rates higher, or were mergers more frequent? What role did feedback play, the energy and momentum dumped into the surrounding gas by supernova explosions and black hole jets? Did feedback suppress star formation, as it does in the modern universe, or did it trigger it, compressing gas clouds and igniting new bursts of star formation in a runaway process? These are not abstract questions. They are the mechanics of cosmic history. Answering them requires more data, more observations, more deep fields, more spectroscopy, more measurements of distances and masses and star formation rates. Webb is providing those measurements, but it is not working alone. Ground-based telescopes, space telescopes in other wavelengths, gravitational wave detectors, all of them are contributing pieces to the puzzle. The picture is incomplete, but it is filling in. One of the more striking aspects of Webb's findings is how little they were anticipated. The telescope was designed to see the first galaxies, the faint proto-galaxies that formed in the cosmic dark ages. It was expected to find small, dim, irregular objects, barely distinguishable from the background noise. Instead, it found massive, bright, structured galaxies, objects that looked like they had no business existing that early. The discovery was not the result of a targeted search for anomalies. It was the result of pointing the telescope at the sky and looking. The early universe simply turned out to be more active than the models predicted. That kind of surprise is rare in modern astronomy. Most discoveries are incremental, confirming predictions or refining measurements. Webb's early galaxy discoveries were not incremental. They were paradigm-shifting. They forced cosmologists to revisit assumptions that had been in place for decades, to question whether the baseline models were tuned to the right part of parameter space, to consider whether the early universe operated under different rules than the modern one. The broader implication is that the universe is still full of surprises. We have been studying the cosmos for centuries, building ever more powerful instruments, collecting ever more precise data, And yet the universe keeps revealing things we did not expect. Dark energy was a surprise. The accelerating expansion was a surprise. The discovery of supermassive black holes in the early universe was a surprise. The crowded, active nature of the first few 100 million years after the Big Bang was a surprise. Each surprise forced a revision of the models, a recalibration of the assumptions, a deeper dive into the physics. The process is ongoing. Webb is not the final word on the early universe. It is the beginning of a new chapter. Future telescopes will push deeper, see fainter objects, resolve smaller structures. Ground-based observatories with mirrors 30 or 40 meters across will complement Webb's infrared observations with high-resolution imaging in the optical and near-infrared. LISA, the space-based gravitational wave detector, will detect supermassive black hole mergers at high redshifts, providing direct evidence for how those black holes grew. The next generation of cosmic microwave background experiments will map the earliest moments after the Big Bang with even greater precision, testing inflation models and searching for signatures of new physics. All of these instruments will build on what Webb has started, filling in the gaps, answering the new questions, and undoubtedly raising new ones. There is also the matter of what Webb has revealed about the limits of observation. The cosmic horizon is not just a theoretical boundary, it is a practical one. Light from galaxies beyond the horizon will never reach us, no matter how long we wait or how sensitive our instruments become. We are fundamentally limited in what we can see, not by technology but by the structure of space-time itself. That limit defines the scope of empirical cosmology. Everything inside the horizon is in principle observable. Everything outside is not. We can theorize about what lies beyond. We can extrapolate from what we see inside, but we cannot observe it directly. The observable universe is all we have. And Webb, by pushing the boundaries of what we can see within that horizon, is showing us how much is packed into that observable volume. Trillions of galaxies, hundreds of sextillion stars, an incomprehensible amount of structure, all of it built from the same starting conditions, all of it governed by the same laws of physics, all of it evolving over nearly 14 billion years. The discoveries Webb has made also highlight how much the universe has changed over its history. The early universe, the one Webb is imaging at high redshifts, does not look like the modern universe. Galaxies were smaller, closer together, more irregular. Star formation rates were higher, black holes were growing faster. The cosmic web was just beginning to take shape. Gas was everywhere, thick and abundant, feeding galaxies at rates far higher than anything we see today. The universe was younger, hotter, denser, more chaotic. Fast forward to the present, and the picture is completely different. Galaxies are larger, more structured, more isolated. Star formation has slowed. Gas has been consumed or expelled. The cosmic web is fully formed, with massive galaxy clusters sitting at the nodes and long filaments of galaxies stretching between them. The universe has aged, it has cooled, it has expanded, and the structures it built in its youth have evolved, merged, and settled into the configurations we see today. Webb is capturing snapshots from different eras of that evolution, allowing astronomers to trace the history of individual galaxies and the cosmic population as a whole. The process is like watching time-lapse footage of a city being built, except the construction spans billions of years and the city is made of stars. One of the more sobering realizations to come out of Webb's observations is how brief humanity's window of observation has been. Modern astronomy, the kind that uses telescopes and quantitative measurements, is only about 400 years old. Cosmology as a rigorous science is less than a century old. The Big Bang model was only confirmed in the 1960s. Dark energy was only discovered in 1998. Webb launched in 2021. We have been seriously studying the universe for a cosmological instant, a blink in the 14 billion year history of the cosmos. And in that brief time we have gone from thinking the Milky Way was the entire universe to realizing that the Milky Way is one of 2 trillion galaxies and the observable universe is only a tiny fraction of the whole. The pace of discovery is staggering. Every decade brings new instruments, new data, new surprises. Webb is the latest step in that progression, but it is not the last. The journey is ongoing, and the destination is unknown. The philosophical weight of understanding the true scale of the universe is difficult to articulate. 2 trillion galaxies, 93 billion light-years, 13.8 billion years. These numbers are so large that they lose meaning. They stop being quantities and become symbols, placeholders for a reality too vast to comprehend. Most people hear these numbers and nod, filing them away as interesting facts, but the full implication does not land. The universe is not just big, it is unimaginably, incomprehensibly, absurdly large. Every star you see in the night sky is part of a single galaxy, one of 2 trillion. Every galaxy contains billions or hundreds of billions of stars. Every star could have planets. Every planet could, in theory, harbor life. The sheer number of places where life could exist, where consciousness could arise, where someone could look up at the night sky and wonder the same things we wonder, is so large that it borders on infinite. And yet we have only found life in one place, Earth. That single data point sits at the center of an enormous question. Are we alone, or is the universe teeming with life, and we simply have not found it yet? Webb is not designed to answer that question directly, but the discoveries it is making about the early universe, about how quickly galaxies formed and how common habitable conditions might have been, are shaping the context in which that question is asked. There is a recurring theme in Webb's findings, one that has shown up in every chapter of this story. The universe is not what we expected. Galaxies formed earlier than expected. Black holes grew faster than expected. The cosmic population is denser than expected. The early universe was more active than expected. The pattern is consistent. Our models, built on decades of careful observation and theoretical work, are good but not perfect. They capture the broad strokes, the overall trajectory, but they miss the details. The early universe was wilder than the baseline models allowed, and Webb is forcing us to update those models in real time. That process is not a failure. It is how science works. You make a prediction, you test it, and when the data come back different than expected, you revise the prediction. The goal is not to be right the first time. The goal is to get closer to the truth with each iteration. Webb is providing the data for the next iteration, and the picture that is emerging is richer, stranger, and more surprising than the one we started with. The legacy of the James Webb Space Telescope will not be a single discovery. It will be the cumulative weight of all the discoveries it has made and will continue to make over the next decade. It will be the images of galaxies at the edge of the observable universe, their light stretched and dimmed by billions of years of cosmic expansion. It will be the spectra showing the chemical fingerprints of the earliest stars, the first heavy elements forged in supernova explosions and scattered into space. It will be the measurements of black hole masses and galaxy structures that forced cosmologists to revisit their assumptions. It will be the deep fields showing trillions of galaxies crowding every patch of sky, a universe far fuller than anyone predicted. And it will be the shift in perspective those discoveries create, the realization that the universe is not just old and vast, but also dynamic, evolving, and fundamentally stranger than the stories we tell about it. We are living in an era of discovery, not the first era and not the last, but one of the most remarkable. The tools we have built, The telescopes and detectors and spacecraft are revealing the universe in unprecedented detail. Webb is the most powerful of those tools, but it is part of a larger effort, a global scientific enterprise aimed at understanding the cosmos and our place in it. The questions we are asking now about the early universe, about dark energy, about the formation of structure, about the possibility of life beyond Earth, are questions that could not have been asked a century ago. The data did not exist, the instruments did not exist, the framework for understanding the universe did not exist. We are asking those questions now because we have reached a point where the tools and the knowledge have converged, where we can point a telescope at the sky and see not just stars but history, not just galaxies but the machinery of cosmic evolution laid bare. That convergence is rare, it is precious, and it is temporary. The window of observation is closing, not for humanity, but for the universe itself. The galaxies we see today will not be visible forever. The cosmic horizon is shrinking, and the future, billions of years from now, will be darker, emptier, lonelier. But that is the future. The present is full of light, full of galaxies, full of questions, and the James Webb Space Telescope, staring into the depths of space and time, is pulling answers out of the ancient light, one photon at a time. The universe has been whispering to us for 14 billion years. Webb is finally teaching us how to listen. And the story those whispers tell, the story of how the cosmos built itself from a featureless fog into the vast structured tapestry we see today, is a story still being written. We are only a few chapters in. The ending is unknown. But the journey, the process of uncovering the universe's secrets and rewriting cosmic history in the light of new evidence is one of the most extraordinary adventures humanity has ever undertaken, and it is far from over. The universe is 93 billion light-years wide, 13.8 billion years old, and filled with 2 trillion galaxies we only just learned to see. Those numbers sit on the page like facts, but they are not facts in the way most facts work. They are doors, thresholds, invitations to step outside the boundary of what your brain was built to comprehend and stand for a moment in the uncomfortable space beyond it. You cannot picture 2 trillion galaxies. You cannot hold 93 billion light-years in your mind as a distance you understand. The numbers are too large. They stop being measurements and become symbols for something your species was never meant to grasp. And yet here you are, a collection of atoms assembled on a wet rock orbiting an average star in an unremarkable galaxy, one of 2 trillion, staring back through time at the light from objects that formed when the universe itself was still a child. You are made of the remnants of dead stars. The carbon in your cells, the oxygen in your lungs, the iron in your blood, all of it was forged inside stars that lived and died billions of years before the sun ignited. You are not separate from the universe. You are a piece of it that learned to think, to wonder, to build telescopes and point them outward into the dark. The James Webb Space Telescope has given us the clearest picture we have ever had of where we came from and what we are part of. It has shown us galaxies that should not exist, black holes that grew too fast, a cosmos that refuses to follow the scripts we wrote for it. And in doing so, it has reminded us of the only truth that matters. The universe does not owe us comprehension. It does not owe us answers. It simply is, vast, strange, indifferent, and more beautiful than any story we could invent. And for a brief moment, in one small corner of